Buchar. Introduction. A universe waiting to shine. Imagine, if you will, a universe cloaked in absolute darkness. Not the darkness of a moonless night where distant stars still pierce the velvet sky. No, this is a darkness more profound than anything you've ever experienced. A darkness so complete, so total, that the very concept of light seems like a distant dream yet to be born. This was our universe, approximately 13.8 billion years ago, in the epoch cosmologists call the Dark Ages. It's a poetic name for a time when the cosmos existed in a state of primordial obscurity, waiting for something extraordinary to happen, waiting for the first stars to ignite. But here's what makes this story truly remarkable. Those first stars, those cosmic pioneers that would eventually illuminate the darkness, didn't exist yet. The universe had all the ingredients, all the raw materials necessary for their birth, but they remained scattered, diffuse, waiting for the precise conditions that would allow them to coalesce into the brilliant furnaces we call stars. This is the story of how that happened. This is the story of cosmic dawn. The significance of first light. Why should we care about the first stars? After all, they existed billions of years ago in a universe so different from our own that it might as well be an alien realm. They're long gone now, their light having traveled across cosmic distances for eons, their matter recycled countless times into new generations of stars, planets, and perhaps even living beings. The answer is simple yet profound. Without those first stars, you wouldn't be here. I wouldn't be here. Nothing we know, nothing we see, nothing we are would exist. The first stars were the cosmic alchemists, the universe's first factories for creating the elements that make up everything around us. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, none of these elements existed in the early universe. They were all forged in the nuclear furnaces of stars, beginning with those first luminous giants. But their importance goes beyond mere chemistry. The first stars fundamentally transformed the universe itself. They ionized the hydrogen gas that filled space, creating bubbles of transparency in an otherwise opaque cosmos. They generated powerful stellar winds that sculpted the distribution of matter on cosmic scales. When they died in spectacular supernova explosions, they seeded the universe with heavy elements and sent shock waves rippling through space, triggering new waves of star formation. In essence, the first stars were the architects of cosmic evolution, the catalysts that set in motion a chain of events leading from a simple uniform universe to the rich, complex cosmos we inhabit today, a cosmos filled with galaxies, planets, and life. A journey through time. To understand how the first stars formed, we must embark on a journey through time unlike any other. We'll travel back to the very beginning, to the first fraction of a second after the Big Bang, when the universe was unimaginably hot and dense. We'll witness the formation of the first atoms, the decoupling of matter and radiation, and the beginning of the Dark Ages. We'll explore how tiny quantum fluctuations, born in the first moments of cosmic time, grew into the seeds of cosmic structure. We'll watch as gravity, that patient sculptor, slowly pulled matter together, creating the first dense clouds of hydrogen and helium gas. We'll witness the moment when these clouds became unstable, collapsing under their own weight, heating up until they reached the critical temperature needed to ignite nuclear fusion. And then we'll see it, the first light. The moment when the first star began to shine, ending the Dark Ages and ushering in a new era in cosmic history. But our journey won't end there. We'll follow the life cycle of these first stars, from their brilliant youth to their violent deaths. We'll see how they transformed the universe, creating the conditions necessary for the formation of new generations of stars. Stars like our own sun, stars that could host planets, stars that could nurture life. This is a story written in the language of physics, told through the medium of cosmic evolution, and recorded in the light that reaches us from the distant past. It's a story that scientists have pieced together through decades of observation, calculation, and theoretical work. and it's a story that continues to unfold as we develop new technologies and new ways of peering into the universe's distant past. The cosmic detectives. How do we know about the first stars? After all, they existed billions of years ago, and their light has long since faded. We can't simply point a telescope at them and observe them directly. Or can we? In a sense, we can. Because light travels at a finite speed, when we look at distant objects in the universe, we're actually looking back in time. The light from a galaxy 1 billion light-years away has taken 1 billion years to reach us. So we're seeing that galaxy as it was 1 billion years ago, not as it is today. This means that if we could look far enough, we could potentially see the first stars themselves. And that's exactly what astronomers are trying to do with powerful new telescopes like the James Webb Space Telescope, launched in 2021. This remarkable instrument is designed to peer deeper into space and therefore further back in time than any telescope before it, potentially allowing us to observe the first generation of stars directly. But even before such direct observations become possible, scientists have developed sophisticated ways of studying the first stars indirectly. They use computer simulations to model how the early universe evolved, incorporating our understanding of physics, gravity, and the behavior of matter under extreme conditions. These simulations can recreate the formation of the first stars in exquisite detail, allowing researchers to test their theories and make predictions about what we should observe. They also study the chemical composition of ancient stars that still exist today. Stars that formed early in the universe's history, though not as early as the very first generation. By analyzing the elements present in these stars, astronomers can infer what the first stars must have been like, because the chemical signatures they left behind tell a story about the conditions in which they formed and died. Additionally, scientists examine the cosmic microwave background radiation, the afterglow of the Big Bang itself, looking for subtle patterns that reveal information about the early universe. They study the large-scale structure of the cosmos, the distribution of galaxies and galaxy clusters, which carries the imprint of processes that occurred when the first stars were forming. Through these various methods, cosmologists have built up a detailed picture of the first stars and the epoch of cosmic dawn. It's a picture that continues to be refined as new observations are made and new theories are developed. And it's a picture that reveals a universe far more dynamic, far more interesting, and far more beautiful than we might have imagined. The cosmic timeline, setting the stage. To fully appreciate the story of the first stars, we need to understand where they fit in the grand timeline of cosmic history. Let's establish some key milestones. Time zero, the Big Bang. This is the beginning of everything we know. Space, time, matter, and energy. In the first fraction of a second, the universe undergoes a period of exponential expansion called inflation, growing from smaller than a subatomic particle to macroscopic size in an instant. First second. The universe is still unimaginably hot and dense. Fundamental particles like quarks and electrons exist in a roiling soup of energy. As the universe expands and cools, quarks combine to form protons and neutrons. Yes, first 3 minutes. Nuclear fusion occurs throughout the universe, creating the first atomic nuclei, mostly hydrogen, some helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, determines the primordial composition of matter in the universe. 80,000 years, recombination. The universe has cooled enough for electrons to combine with atomic nuclei, forming the first neutral atoms. This is a crucial moment because it makes the universe transparent to light for the first time. Before this, photons were constantly scattered by free electrons, making the universe opaque like a dense fog. After recombination, light can travel freely through space. 380,000 to 100 million years, the Dark Ages. This is the period we're most interested in. The universe is filled with neutral hydrogen and helium gas, but no stars have formed yet. It's dark, cold, and relatively simple, but not for long. 100–200 million years, cosmic dawn. The first stars begin to form, ending the Dark Ages. This is the epoch we'll explore in detail throughout this script. 100 million years, the epoch of reionization. The first stars and galaxies produce enough ultraviolet radiation to ionize most of the hydrogen in the universe, fundamentally changing its properties. 1 billion years onward. Galaxies grow and evolve, new generations of stars form, and the universe gradually takes on the appearance we see today. Understanding this timeline is crucial because it shows us that the first stars didn't form immediately after the Big Bang. There was a waiting period, a time when the universe needed to cool down, expand, and develop the conditions necessary for star formation. The Dark Ages weren't just an empty interval. They were a time of preparation, when the seeds of cosmic structure were slowly growing, setting the stage for the dramatic transformation to come. The ingredients of stars. Before we can understand how the first stars formed, we need to know what they were made of. And here's where the story gets interesting, because the first stars were fundamentally different from stars like our Sun. When we analyze the composition of our Sun, we find it's made of about 73% hydrogen, 25% helium, and 2% heavier elements, what astronomers call metals, even though this category includes elements like carbon, oxygen, and nitrogen that chemists wouldn't classify as metals. These heavier elements are crucial for star formation in the modern universe because they help gas clouds cool down and collapse. But the first stars had none of these heavier elements. They formed from the primordial gas created in the Big Bang, which was composed of roughly 75% hydrogen, 25% helium, and trace amounts of lithium. That's it. No carbon, no oxygen, no iron, no silicon. Just the three lightest elements in the periodic table. This might seem like a minor detail, but it had profound consequences for how the first stars formed and what they were like. Without heavier elements to help the gas cool efficiently, the first star-forming clouds had to be much more massive than modern star-forming clouds. This meant the first stars themselves were likely enormous, perhaps 100 to 1,000 times more massive than our Sun, compared to the typical range of 0.1 to 100 solar masses for stars forming today. These massive first stars would have been incredibly hot and luminous, burning through their nuclear fuel at a prodigious rate. While our Sun will shine for about 10 billion years, the first stars might have lived for only a few million years before exhausting their fuel and dying in spectacular supernova explosions. But we're getting ahead of ourselves. Before these stars could live and die, they first had to form. And that process began with the simplest of ingredients, hydrogen and helium, spread thinly across the expanding universe, waiting for gravity to work its magic. The role of dark matter. There's another crucial ingredient in the story of the first stars, one that's invisible and mysterious: dark matter. Dark matter is one of the great puzzles of modern cosmology. We can't see it directly because it doesn't emit, absorb, or reflect light. We know it exists only through its gravitational effects on visible matter and light. And remarkably, it makes up about 85% of all the matter in the universe. The ordinary matter that makes up stars, planets, and people, the matter we can see and touch, is just a small fraction of the total. In the early universe, dark matter played a crucial role in the formation of the first stars. Because dark matter doesn't interact with light or ordinary matter except through gravity, it began clumping together earlier than ordinary matter. Dark matter created the gravitational scaffolding, the framework upon which ordinary matter could collect and eventually form stars. Think of it like this. Dark matter created the valleys, and ordinary matter flowed into them like water flowing downhill. The densest concentrations of dark matter became the sites where the first stars would eventually form. This is why scientists sometimes call dark matter the invisible architect of cosmic structure. Without it, the universe would look completely different. Galaxies might not exist, or they might be much smaller and less numerous, and the first stars might have taken much longer to form, if they formed at all. So as we tell the story of the first stars, we must remember that there's an invisible partner in this cosmic dance, a silent collaborator that shaped the destiny of the universe without ever revealing itself directly to our observations. Nihi, The question that drives us. Why do we care so much about understanding the first stars? What drives scientists to dedicate their careers to studying objects that existed billions of years ago and can never be directly touched or visited? The answer lies in a fundamental human impulse, the desire to understand our origins. Just as individuals want to know about their family history and societies preserve their cultural heritage, humanity as a whole seeks to understand where we came from and how we got here. The first stars are part of our cosmic family tree. They're our ancestors in a very real sense, because the atoms in our bodies were forged in stars, not the first stars themselves, but later generations of stars that formed from material enriched by the first stars' deaths. When we study the first stars, we're studying the first chapter in a story that eventually leads to us. We're tracing the chain of events that transformed a simple, uniform universe into a complex cosmos capable of producing planets, life, and consciousness. But beyond this philosophical motivation, there are practical reasons to study the first stars. Understanding how they formed helps us refine our models of cosmology and astrophysics. It tests our theories about how gravity works on cosmic scales, how matter behaves under extreme conditions, and how structures form and evolve in the universe. Every new discovery about the first stars potentially reveals something new about the fundamental laws of physics. And in a field where we're still grappling with mysteries like dark matter and dark energy, every piece of information is valuable. The promise of discovery. We live in an extraordinary time for the study of the first stars. New telescopes and instruments are giving us unprecedented views of the early universe. Computer simulations are becoming more sophisticated, allowing us to model the formation of the first stars in greater detail than ever before. And theoretical understanding is advancing rapidly as researchers develop new ideas about how the first stars formed and evolved. The James Webb Space Telescope, in particular, has opened a new window on the early universe. Its infrared vision allows it to peer through cosmic dust and see objects so distant that their light has been traveling toward us for more than 13 billion years. While we haven't yet definitively observed the first stars themselves, we're getting tantalizingly close, seeing galaxies that formed when the universe was only a few 100 million years old. Galaxies that must contain stars from the second or third generation after the very first. In the coming years and decades, we can expect major breakthroughs in our understanding of the first stars. We might directly observe them for the first time. We might detect the gravitational waves produced when the first black holes, formed from the deaths of the first stars, merged together. We might find chemical signatures in ancient stars that tell us exactly what the first stars were like. Each discovery will add a new piece to the puzzle, bringing us closer to a complete understanding of how the first stars formed and how they shaped the universe we inhabit today. The structure of our story. As we proceed through this script, we'll follow a logical progression that mirrors the actual sequence of events in cosmic history. We'll begin with the Big Bang itself, understanding the initial conditions that set everything in motion. We'll explore the first moments of cosmic time when the fundamental forces and particles came into being. Then, we'll move into the Dark Ages, that long period of waiting when the universe was dark but not empty, when the seeds of structure were slowly growing in the darkness. We'll examine how gravity began to pull matter together, creating the first dense clouds of gas that would eventually collapse to form stars. We'll witness the moment of first light when nuclear fusion ignited in the core of the first star, ending the Dark Ages forever. We'll explore what these first stars were like, their size, temperature, luminosity, and lifespan. We'll see how they transformed the universe through their radiation and their deaths, creating the conditions necessary for new generations of stars to form. And finally, we'll trace their legacy, showing how the first stars set in motion a chain of events that eventually led to the formation of galaxies, planets, and life. Throughout this journey, we'll encounter some of the most profound questions in science. How did something come from nothing? How did order emerge from chaos? How did the universe go from simple to complex? And ultimately, How did a universe that began as a featureless expanse of hydrogen and helium gas eventually produce beings capable of contemplating their own origins? The wonder of cosmic evolution. Before we dive into the details, let's take a moment to appreciate the sheer wonder of what we're about to explore. The story of the first stars is, in many ways, the story of how the universe learned to create complexity. It's about how gravity, acting on tiny imperfections in an otherwise smooth distribution of matter, created structure where there was none. It's about how nuclear fusion transformed simple elements into complex ones. It's about how energy and matter, following the laws of physics, organized themselves into increasingly intricate patterns. This is a story without a storyteller, a design without a designer, a creation that created itself through the blind operation of natural law. And yet, the result is something of breathtaking beauty and complexity, a universe filled with stars and galaxies, with planets and moons, with atoms and molecules capable of assembling themselves into living organisms. The first stars were the first step in this journey from simplicity to complexity. They were the universe's first experiment in creating something new, something that had never existed before. And they succeeded beyond measure, setting in motion a process of cosmic evolution that continues to this day. As we explore their story, we're not just learning about ancient history. We're learning about the processes that shaped our world and made our existence possible. We're discovering the deep connections between the largest and smallest scales of reality, between the quantum fluctuations of the early universe and the galaxies we see in the night sky. We're uncovering the hidden order in apparent chaos, the simplicity underlying complexity, the unity within diversity. This is the story of cosmic dawn. This is the story of how the first stars formed, and it begins, as all great stories do, at the beginning. The darkness before dawn. Picture the universe. 380,000 years after the Big Bang. The cosmic microwave background radiation has just been released, carrying with it a snapshot of the universe at that moment, a snapshot we can still observe today, encoded in the faint microwave radiation that fills all of space. At this moment, the universe is remarkably uniform. If you could zoom out and look at the distribution of matter on large scales, you'd see an almost perfectly smooth distribution of hydrogen and helium gas. The temperature is about 3 Kelvin. Hot enough to glow with a dull red light, like the heating element of an electric stove. But you wouldn't see this glow because there's no one to see it. No stars, no planets, no life. Just gas, expanding and cooling as the universe grows. And yet, hidden within this apparent uniformity are tiny variations in density, regions where the gas is slightly denser than average, and regions where it's slightly less dense. These variations are tiny. Only about 1 part in 100,000, but they're crucial. They're the seeds from which all cosmic structure will grow. As time passes, the universe continues to expand and cool. The gas that once glowed red fades to infrared, then to microwave, then to radio wavelengths. The universe grows dark. This is the beginning of the Dark Ages, and it's here that our story truly begins. Because in this darkness, in this apparent emptiness, the first stars are waiting to be born. The ingredients are all present. The stage is set. All that's needed is time for gravity to work its patient magic, pulling matter together, creating the conditions for the first light to shine. And so we wait, in the darkness, for the cosmic dawn. The moment of creation. How does a universe begin? It's perhaps the most profound question we can ask, touching on the boundaries between science and philosophy, between the knowable and the unknowable. Yet modern cosmology has given us a remarkable answer, one that's both scientifically rigorous and almost mythologically powerful in its implications. The universe began in an event we call the Big Bang, approximately 13.8 billion years ago. But this name is somewhat misleading. It wasn't an explosion in space, it was an explosion of space itself. Space, time, matter, and energy all came into existence simultaneously in this singular event. Before the Big Bang, there was no before. Time itself began at this moment, so it makes no sense to ask what came before it any more than it makes sense to ask what's north of the North Pole. The question itself becomes meaningless. In the first instant of cosmic time, a period so brief that it defies human comprehension, lasting only 10.43 seconds, that's a decimal point followed by 42 zeros and then a 1. The universe existed in a state that our current physics cannot fully describe. This is called the Planck epoch, named after physicist Max Planck, and during this time, the universe was so hot and dense that quantum effects dominated even gravity. We don't have a complete theory that can describe this epoch because it requires a quantum theory of gravity, something physicists are still working to develop. But we can describe what happened immediately afterward, and it's a story of breathtaking transformation. Inflation, the universe's growth spurt. After the Planck epoch, something extraordinary happened. The universe underwent a period of exponential expansion called cosmic inflation. In a tiny fraction of a second, perhaps by 10^36 to 10^32 seconds after the Big Bang, the universe grew by a factor of at least 10^26, expanding from smaller than a subatomic particle to roughly the size of a grapefruit. This might sound like science fiction, but inflation theory solves several major puzzles about the universe we observe today. It explains why the universe is so uniform on large scales, because regions that are now on opposite sides of the observable universe were once close enough to exchange energy and reach the same temperature. It explains why the universe is so flat geometrically, because inflation stretched out any curvature that might have existed initially. And crucially for our story, it explains where the tiny density variations came from that would eventually grow into galaxies and stars. During inflation, quantum fluctuations, the random jitter that exists at the smallest scales due to Heisenberg's uncertainty principle, were stretched to cosmic scales. These fluctuations became frozen into the fabric of space itself, creating regions that were slightly denser or less dense than average. These variations were incredibly small, but they were the seeds from which all cosmic structure would grow. Think of it like this. Imagine you have a balloon with tiny wrinkles on its surface. As you inflate the balloon, those wrinkles get stretched out and magnified. Similarly, inflation took quantum scale fluctuations and stretched them to scales of light years and beyond. These stretched fluctuations became the blueprint for the universe's structure, the pattern that would determine where galaxies would form, where the first stars would ignite, and ultimately, where we would exist. Inflation ended as suddenly as it began, and the universe transitioned into a more sedate phase of expansion that continues to this day. But the seeds it planted would shape the cosmos forever. The primordial soup. After inflation ended, the universe was filled with an incredibly hot, dense soup of fundamental particles and energy. The temperature was trillions of degrees, far hotter than the core of any star. At these temperatures, matter as we know it couldn't exist. Instead, the universe was filled with a plasma of quarks, gluons, electrons, photons, and other fundamental particles, all in a state of constant interaction. This might seem chaotic, but it was actually a time of great symmetry. The fundamental forces that govern the universe today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified or closely related at these high energies. As the universe expanded and cooled, these forces separated from each other in a process called symmetry breaking, taking on the distinct characteristics we observe today. In the first microsecond after the Big Bang, the universe cooled enough for quarks to combine into protons and neutrons, the building blocks of atomic nuclei. This transition, called the quark-hadron transition, was a crucial step in creating the matter that would eventually form stars and galaxies. But the universe was still far too hot for these protons and neutrons to combine into atomic nuclei. They existed as free particles, constantly buffeted by high-energy photons and other particles in the primordial soup. The universe was opaque during this time, like a dense fog, because photons couldn't travel far before being scattered by free electrons. Big Bang nucleosynthesis, forging the first elements. About 1 second after the Big Bang, the universe had cooled to about 10 billion degrees Kelvin, still incredibly hot but cool enough for something remarkable to happen. Protons and neutrons began to stick together, forming the first atomic nuclei. This process, called Big Bang nucleosynthesis, lasted for only about 17 minutes, but in that brief window, the universe created most of the helium that exists today, along with trace amounts of deuterium, heavy hydrogen, helium-3, and lithium-7. Here's how it worked. At these temperatures, when a proton and neutron collided, they could stick together to form deuterium, one proton and one neutron. Deuterium could then capture another neutron to form tritium, one proton and two neutrons, or another proton to form helium-3, two protons and one neutron. These could then combine to form helium-4, two protons and two neutrons, the most common form of helium. The process was remarkably efficient. By the time the universe had cooled too much for fusion to continue, about 25% of the ordinary matter in the universe, by mass, had been converted into helium-4, with the rest remaining as hydrogen. There were also tiny amounts of deuterium, helium-3, and lithium-7. This might not sound like much, but it's one of the great triumphs of modern cosmology. When we observe the universe today, we find that the oldest, most pristine gas clouds have almost exactly this composition, about 75% hydrogen and 25% helium by mass, with trace amounts of the other light elements. This agreement between theory and observation is powerful evidence that our understanding of the Big Bang is fundamentally correct. But notice what didn't form during Big Bang nucleosynthesis. Heavier elements like carbon, oxygen, nitrogen, iron, and all the others that make up the periodic table. These elements didn't exist yet. They would have to wait for the first stars to form, because only in the nuclear furnaces of stars could these heavier elements be created. This is why the first stars are so important. They were the universe's first factories for creating chemical complexity. Before them, the universe was chemically simple, just hydrogen, helium, and a tiny bit of lithium. After them, the universe would be enriched with dozens of new elements, opening up possibilities that didn't exist before. The photon epoch, a universe of light. After Big Bang nucleosynthesis ended, the universe entered a long period dominated by radiation. During this photon epoch, which lasted for about 380,000 years, the universe was filled with an incredibly bright light. Photons outnumbered matter particles by about 1,000,000,000 to 1. But you still couldn't see anything, because the universe was opaque. Free electrons scattered photons constantly, preventing light from traveling in straight lines. It was like trying to see through a thick fog, except the fog was everywhere, and there was no clear air beyond it. During this time, the universe continued to expand and cool. The temperature dropped from billions of degrees to thousands of degrees. The density decreased as space stretched, but the fundamental character of the universe remained the same. A hot, dense, opaque plasma of matter and radiation. This epoch is important for our story because it set the stage for what came next. As the universe cooled, it was approaching a critical threshold, the temperature at which electrons could combine with atomic nuclei to form neutral atoms. When that happened, the universe would undergo a transformation as dramatic as any in its history. Recombination. Let there be transparency. About 380,000 years after the Big Bang, when the temperature had dropped to about 3,000 Kelvin, something remarkable happened. Electrons, which had been zipping around freely, began to combine with atomic nuclei to form neutral atoms. This process is called recombination, though the name is a bit misleading. The electrons weren't actually recombining with nuclei they'd been attached to before, because they'd never been attached in the first place. But the name has stuck. Recombination was a gradual process, taking perhaps tens of thousands of years to complete, but its effects were dramatic. As more and more electrons became bound in atoms, there were fewer and fewer free electrons to scatter photons. The universe became transparent. Suddenly, light could travel freely through space. The photons that had been trapped constantly scattered by free electrons, were released. They've been traveling through the universe ever since, and we can still detect them today as the cosmic microwave background radiation, the afterglow of the Big Bang. This is one of the most important observations in all of cosmology. When we detect the cosmic microwave background, we're seeing light that has been traveling toward us for more than 13 billion years. We're seeing the universe as it was when it was only 380,000 years old, a baby by cosmic standards. And what we see is remarkable. The cosmic microwave background is incredibly uniform, with a temperature of about 2.725 Kelvin in every direction we look. But it's not perfectly uniform. There are tiny variations in temperature, about 1 part in 100,000, that correspond to regions of slightly different density in the early universe. These tiny variations are the seeds of cosmic structure, the same seeds that were planted during inflation. They show us where the universe was slightly denser or less dense than average, and they predict where the first stars would eventually form because the densest regions would be the first to collapse under their own gravity. The universe revealed. Let's pause for a moment and imagine what the universe looked like at the moment of recombination. If you could somehow exist at this time and look around, what would you see? First, you'd see light, lots of it. The universe would glow with a dull red color, like the heating element of an electric stove. This is because the temperature was about 3,000 Kelvin, which corresponds to red light in the visible spectrum. But the light would be coming from everywhere at once. There would be no stars, no galaxies, no distinct sources of light. The glow would be uniform in all directions, filling all of space. If you had instruments sensitive enough to detect tiny variations in the brightness of this glow, you'd see a subtle pattern, regions that were slightly brighter or dimmer than average. These variations would be incredibly small, only about 0.1% different from the average brightness. But they would be there, and they would be important. These brighter regions correspond to areas where the gas was slightly denser and hotter than average. The dimmer regions correspond to areas where the gas was slightly less dense and cooler. These variations might seem insignificant, but they're the seeds from which galaxies and stars would grow. As you watched, and you'd have to watch for millions of years, you'd see the glow gradually fade. The universe is expanding, and as it expands, the light gets stretched to longer wavelengths. The red glow would fade to infrared, then to microwave, then to radio wavelengths. The universe would grow dark. This is the beginning of the Dark Ages, the period we introduced in Chapter 1. And it's here that the real story of the first stars begins. The composition of the primordial universe. At the end of recombination, the universe had a well-defined composition. Let's inventory what existed. Hydrogen. About 75% of the ordinary matter by mass. Most of this was in the form of neutral hydrogen atoms, one proton with one electron orbiting it. This is the simplest and most abundant element in the universe, and it would be the primary fuel for the first stars. Helium. About 25% of the ordinary matter by mass. Most of this was helium-4, with 2 protons and 2 neutrons in the nucleus and 2 electrons orbiting. There were also trace amounts of helium-3, with 2 protons and 1 neutron. Deuterium. A tiny fraction, about 0.022% by mass. Deuterium is heavy hydrogen, with 1 proton and 1 neutron in the nucleus. It's important because it's easily destroyed in stars, so the amount of deuterium we observe today tells us about how much star formation has occurred. Lithium-7. An even tinier fraction, about 0.001% by mass, lithium-7, has 3 protons and 4 neutrons. Like deuterium, it's easily destroyed in stars, making it a useful tracer of cosmic history. Electrons. Equal in number to the total number of protons, ensuring that the universe was electrically neutral overall. Photons. About 1 billion photons for every proton or neutron. These photons would eventually become the cosmic microwave background radiation we detect today. Neutrinos. Also about 1 billion for every proton or neutron. Neutrinos are ghostly particles that barely interact with matter, and they've been streaming freely through the universe since about 1 second after the Big Bang. Dark matter. About 85% of the total matter in the universe. We don't know exactly what dark matter is made of, but we know it exists because of its gravitational effects. It doesn't interact with light or ordinary matter except through gravity, so it was invisible then, and remains invisible now. Dark energy. About 68% of the total energy density of the universe today, though it was less important in the early universe. Dark energy is a mysterious form of energy that causes the expansion of the universe to accelerate. We don't fully understand what it is, but we can measure its effects. This was the raw material from which the first stars would form. It might seem like a simple recipe, just hydrogen, helium, and a bit of lithium. But it was enough. Given time and gravity, this simple mixture would transform into something extraordinary. The seeds of structure. Remember those tiny variations in density we mentioned, the 1 part in 100,000 fluctuations that we see in the cosmic microwave background? These variations are crucial to our story, so let's understand where they came from and what they mean. During the inflationary epoch, quantum fluctuations were stretched to cosmic scales. These fluctuations created regions where the density of matter and energy was slightly higher or lower than average. When inflation ended, these variations were frozen into the fabric of space. As the universe evolved through the photon epoch and recombination, these density variations persisted. In fact, they grew slightly due to gravitational instability. Regions that were denser than average attracted more matter, becoming even denser, while regions that were less dense lost matter to their surroundings, becoming even less dense. But this growth was slow during the photon epoch because radiation pressure resisted gravitational collapse. Photons exert pressure when they bounce off matter, and in the early universe, there were so many photons that this pressure was significant. It prevented matter from clumping together too quickly. However, after recombination, this changed. Once the photons decoupled from matter and began streaming freely through space, they no longer exerted significant pressure on the matter. Gravity could finally work unimpeded, pulling matter together into increasingly dense clumps. This is when the growth of structure really began. The tiny variations in density started to grow more rapidly, with denser regions attracting more and more matter from their surroundings. But there's a twist to this story, and it involves dark matter. Aquí, the role of dark matter in structure formation. Dark matter doesn't interact with photons at all. It doesn't emit, absorb, or scatter light. This means that even before recombination, dark matter wasn't affected by radiation pressure. It could begin clumping together under gravity much earlier than ordinary matter. By the time of recombination, dark matter had already formed significant structures, regions of enhanced density that we call dark matter halos. These halos created gravitational wells, like valleys in a landscape, into which ordinary matter could flow. After recombination, when ordinary matter was finally free to respond to gravity without interference from radiation pressure, it began falling into these dark matter halos. The ordinary matter collected in the centers of the halos, where it would eventually become dense enough to form the first stars. This is why dark matter is so important for the formation of the first stars. Without dark matter, structure formation would have proceeded much more slowly. The first stars might have taken billions of years to form instead of hundreds of millions of years. The universe might look completely different today. Dark matter provided the gravitational scaffolding, the framework upon which ordinary matter could build. It was the invisible architect of cosmic structure, shaping the universe in ways we're only beginning to fully understand. The cosmic web begins to form. As matter began to clump together under gravity, it didn't do so randomly. Instead, it formed a pattern, a cosmic web of filaments and sheets with dense nodes at the intersections. This structure emerged naturally from the initial density variations and the way gravity works. Regions that were slightly denser than average attracted matter from their surroundings, but they didn't attract matter equally from all directions. Instead, matter flowed preferentially along certain directions, creating filaments, long, thin structures of enhanced density. Where multiple filaments intersected, the density became even higher, creating nodes. These nodes would become the sites of the first galaxies and the first stars. This cosmic web structure is still visible in the universe today. When we map the distribution of galaxies on large scales, we see that they are not distributed randomly. Instead, they're arranged in a web-like pattern, with filaments of galaxies separated by vast voids containing very few galaxies. This pattern was set in motion in the early universe during the Dark Ages as matter began to respond to the gravitational pull of the density variations created during inflation. The first stars would form at the densest nodes of this emerging cosmic web. The Dark Ages, a time of preparation. After recombination, the universe entered the period we call the Dark Ages. This name is apt because the universe was literally dark. There were no stars yet to provide light, and the cosmic microwave background had faded from visible light to infrared and beyond. But the Dark Ages weren't a time of stagnation. Far from it. This was a time of preparation, when the conditions necessary for star formation were slowly developing. Gravity was pulling matter together, creating increasingly dense clumps. Dark matter halos were growing, attracting ordinary matter into their gravitational wells. The cosmic web was taking shape, with filaments and nodes emerging from the initially smooth distribution of matter. The temperature of the gas was dropping as the universe expanded. At recombination, the temperature was about 3,000 Kelvin. By the time the first stars formed, hundreds of millions of years later, the background temperature of the universe had dropped to about 20-30 Kelvin, cold enough that the gas could cool and collapse more easily. But the gas wasn't cooling uniformly. In the densest regions, where matter was clumping together, gravitational compression was heating the gas. This created a competition between cooling, due to the expansion of the universe and radiation of energy, and heating, due to gravitational compression. For a gas cloud to collapse and form a star, cooling must win. The gas must be able to radiate away the heat generated by gravitational compression. Otherwise, the pressure from the hot gas will resist further collapse, preventing the gas from becoming dense enough to ignite nuclear fusion. In the modern universe, heavy elements like carbon and oxygen help gas clouds cool efficiently. These elements can radiate energy very effectively, allowing gas clouds to cool rapidly and collapse to form stars. But in the primordial universe, there were no heavy elements. The gas was pure hydrogen and helium, with just a trace of lithium. These elements don't cool as efficiently as heavy elements, which meant that primordial gas clouds had to be more massive to collapse and form stars. This is one of the key differences between the first stars and modern stars. The first stars formed from more massive gas clouds, and they themselves were more massive as a result. Molecular hydrogen, the cooling agent. Even though hydrogen and helium don't cool as efficiently as heavy elements, they can still cool, and there's one form of hydrogen that's particularly important for cooling in the primordial universe, molecular hydrogen, or H2. Molecular hydrogen consists of two hydrogen atoms bonded together. It can form when two hydrogen atoms collide in the presence of a third particle, which can be another hydrogen atom, a helium atom, or an electron, that can carry away the excess energy. Once formed, molecular hydrogen can cool gas clouds very effectively through a process called rotational cooling. The molecule can rotate, and when it collides with other particles, it can be excited to higher rotational states. When it then drops back to lower rotational states, it emits infrared photons, carrying energy away from the gas cloud. This might sound like a minor detail, but it's crucial. Without molecular hydrogen, the primordial gas clouds might not have been able to cool enough to collapse and form stars. The first stars might never have formed, and the universe might have remained dark indefinitely. Fortunately, molecular hydrogen did form in the densest regions of the early universe. As gas clouds became denser, the rate of H2 formation increased, and as H2 accumulated, it allowed the gas to cool more efficiently, enabling further collapse. This created a positive feedback loop. Denser gas formed more H2, which allowed more cooling, which allowed more collapse, which created even denser gas. This feedback loop was essential for the formation of the first stars. Noordverwerks, the critical threshold. For a gas cloud to collapse and form a star, it must exceed a critical mass called the Jeans mass, named after physicist James Jeans, who first calculated it in 1902. The Jeans mass depends on the temperature and density of the gas. Hotter gas has a higher Jeans mass because the thermal pressure resists collapse more strongly. Denser gas has a lower Jeans mass because gravity is stronger. In the primordial universe, the Jeans mass was quite high, perhaps 1,000 to 10,000 times the mass of our Sun. This is because the gas was relatively hot, even after cooling by molecular hydrogen, and relatively diffuse, even in the densest regions. This meant that the first stars had to form from very massive gas clouds, and when these clouds collapsed, they formed very massive stars, much more massive than typical stars forming today. Modern stars have masses ranging from about 0.08 solar masses, the minimum mass needed to sustain hydrogen fusion, to about 150 solar masses, the maximum mass that can form without becoming unstable. Most stars are on the lower end of this range. Our Sun at 1 solar mass is actually more massive than about 95% of stars. But the first stars were different. Computer simulations suggest they had masses ranging from about 100 to 1,000 solar masses, with some possibly even larger. These were true giants, massive beyond anything we see forming in the universe today. The stage is set by the end of the Dark Ages. All the pieces were in place for the first stars to form. Dark matter, halos, had grown to sufficient size, creating deep gravitational wells. Ordinary matter had flowed into these halos, creating dense concentrations of hydrogen and helium gas. Molecular hydrogen had formed in the densest regions, allowing the gas to cool. Some gas clouds had exceeded the Jeans mass, making them unstable to gravitational collapse. The universe was poised on the brink of transformation. The Dark Ages were about to end. The first stars were about to be born. But before we witness that moment, the moment of cosmic dawn, we need to understand the Dark Ages in more detail. We need to explore what the universe was like during this long period of waiting and how the conditions for star formation gradually developed. That's the story we'll tell in the next chapter. For now, let's appreciate what we've learned. The universe began in a hot, dense state, the Big Bang. It underwent a period of exponential expansion called inflation, which planted the seeds of cosmic structure. It cooled and expanded, creating the first atomic nuclei through Big Bang nucleosynthesis. It became transparent at recombination, releasing the cosmic microwave background radiation. And it entered the Dark Ages, a period of preparation when gravity slowly pulled matter together, setting the stage for the formation of the first stars. This is the foundation of our story. Everything that follows, the formation of the first stars, their transformation of the universe, and ultimately the emergence of galaxies, planets, and life, builds on this foundation. The universe started simple. Just hydrogen, helium, and a bit of lithium, spread almost uniformly through space. But hidden within this simplicity were the seeds of complexity, tiny variations in density that would grow into galaxies and stars. The laws of physics, acting on this simple initial state, would create a universe of breathtaking complexity and beauty. And it all began with the Big Bang. A universe in waiting. Imagine a universe without light, not the darkness of night, where stars still shine and the moon casts its gentle glow. Not even the darkness of a cave, deep underground, where the concept of light still exists as a memory or a possibility. No, imagine a darkness more complete, a universe where light itself has faded away, where no stars have yet formed to pierce the gloom, where the only radiation is the fading afterglow of creation itself, stretched to wavelengths too long for any eye to see. This was the universe during the Dark Ages, the period from about 380,000 years to roughly 100–200 million years after the Big Bang. It's called the Dark Ages, not just because the universe was literally dark, but also because it's a period we know relatively little about. We can't observe it directly because there were no stars to see, no galaxies to study. It's a gap in our cosmic history, a chapter written in invisible ink. But this darkness wasn't empty. Far from it. During the Dark Ages, the universe was a hive of activity, a cosmic construction site where the foundations of all future structure were being laid. Gravity was at work, patiently pulling matter together, creating the conditions that would eventually allow the first stars to form. This chapter is about that period of waiting, that time of preparation. It's about how the universe transformed itself from a nearly uniform sea of gas into a complex web of structure, setting the stage for the cosmic dawn. The fading light. Let's begin at the moment of recombination, when the universe became transparent and the cosmic microwave background radiation was released. At this moment, the universe was filled with light. Photons that had been trapped, constantly scattered by free electrons, were suddenly free to travel through space. If you could see this light, it would appear as a dull red glow, coming from every direction at once. The temperature of this radiation was about 3 Kelvin, corresponding to the peak wavelength of red light. But as the universe continued to expand, something happened to this light. The expansion of space stretched the wavelengths of the photons, shifting them toward the red end of the spectrum and beyond. This process, called cosmological redshift, is one of the fundamental consequences of living in an expanding universe. Over time, the red glow faded to infrared, then to microwave, then to radio wavelengths. The universe grew dark, at least to any hypothetical observer with eyes like ours. The light was still there. It's still there today as the cosmic microwave background radiation, but it had been stretched to wavelengths we can't see without special instruments. This fading of the light marked the beginning of the Dark Ages. The universe had gone from a glowing plasma to a dark, cold expanse of neutral gas. The temperature had dropped from 3 Kelvin to a few dozen Kelvin. The density had decreased as space expanded, and yet, hidden within this apparent emptiness, the seeds of future stars were beginning to grow. The cosmic web takes shape. During the Dark Ages, the most important process occurring in the universe was the growth of structure through gravitational instability. Let's understand how this worked. Remember the tiny density variations we discussed in previous chapters, the 1 part in 100,000 fluctuations that were planted during inflation and preserved through recombination. These variations might seem insignificant, but they were the seeds from which all cosmic structure would grow. Here's the key insight. Regions that are denser than average have stronger gravity. This stronger gravity attracts matter from the surrounding regions, making the dense region even denser. Meanwhile, regions that are less dense than average lose matter to their surroundings, becoming even less dense. This is called gravitational instability, and it's a runaway process. Small differences in density grow into large differences over time, but the growth isn't uniform in all directions. Gravity pulls matter preferentially along certain paths, creating a web-like structure of filaments and sheets. Where filaments intersect, the density becomes very high, creating nodes that will eventually become the sites of galaxy formation. This cosmic web structure is one of the most beautiful and fundamental features of our universe. It emerges naturally from the initial density fluctuations and the action of gravity, without any need for special conditions or fine-tuning. It's a pattern that's written into the fabric of the cosmos. During the Dark Ages, this cosmic web was taking shape. Dark matter, which had been clumping together since before recombination, formed the skeleton of the web. Ordinary matter, newly freed from the influence of radiation pressure, began flowing into the dark matter halos, collecting in the densest regions. If you could somehow watch the Dark Ages and fast forward, you'd see a remarkable transformation. The initially smooth distribution of matter would develop structure, with filaments emerging and growing, nodes forming at intersections, and voids opening up between the filaments. It would look like a cosmic spider's web being woven by invisible hands. Dark matter, halos, the cradles of stars. Let's zoom in on one of the nodes in this cosmic web, a region where multiple filaments intersect, creating a particularly dense concentration of matter. This is where the first stars will eventually form, so it's worth understanding in detail. At the center of this node is a dark matter halo, a roughly spherical concentration of dark matter held together by its own gravity. The halo formed early in the Dark Ages as dark matter particles in this region began to clump together under gravity. As the halo grew, it attracted more dark matter from its surroundings. The halo's gravity also attracted ordinary matter, hydrogen and helium gas, which began flowing into the halo along the filaments of the cosmic web. This ordinary matter didn't distribute itself uniformly within the halo. Instead, it collected in the center where the gravitational pull was strongest. As more and more gas flowed in, the central concentration became denser and denser. But there was a problem. As the gas became denser, it also became hotter. This is because gravitational compression releases energy, heating the gas, and hot gas has high pressure, which resists further compression. For a star to form, the gas needs to become incredibly dense enough that the temperature and pressure at the center are high enough to ignite nuclear fusion. But if the gas can't cool down, it can't compress to these extreme densities. The pressure will balance gravity, and the gas will settle into a stable configuration without forming a star. This is where cooling becomes crucial. The gas must be able to radiate away the heat generated by gravitational compression. Only then can it continue to collapse, becoming dense enough to form a star. The cooling crisis. In the modern universe, gas clouds cool very efficiently thanks to heavy elements like carbon, oxygen, and nitrogen. These elements have complex atomic structures with many energy levels, allowing them to absorb and emit photons at a wide range of wavelengths. This makes them excellent coolants. They can radiate energy very effectively, allowing gas clouds to cool rapidly. But in the primordial universe, there were no heavy elements. The gas was pure hydrogen and helium with just a trace of lithium. These elements have simpler atomic structures and can't cool as efficiently. Atomic hydrogen can cool through several processes. Lyman alpha emission. When an electron in a hydrogen atom drops from the second energy level to the first, it emits a photon with a wavelength of 121.6 nanometers in the ultraviolet. Collisional excitation and de-excitation. Hydrogen atoms can be excited to higher energy levels through collisions, then emit photons as they drop back to lower levels. Helium can also cool through similar processes, though it's less efficient than hydrogen because helium atoms are more tightly bound. But these atomic cooling processes aren't very efficient at the temperatures and densities typical of primordial gas clouds. The gas would cool too slowly, and the pressure would prevent it from collapsing to the densities needed for star formation. This is where molecular hydrogen comes in. Molecular hydrogen. The key to cooling. Molecular hydrogen, H2, consisting of two hydrogen atoms bonded together, is the key to understanding how the first stars formed. It's a simple molecule, but it has a remarkable property. It can cool gas very efficiently through rotational transitions. Here's how it works. A molecule can rotate, spinning around its center of mass. Quantum mechanics tells us that this rotation is quantized. The molecule can only rotate at certain specific rates, corresponding to different rotational energy levels. When an H2 molecule collides with another particle, a hydrogen atom, a helium atom, or another H2 molecule, it can be excited to a higher rotational level. Later, it can drop back to a lower rotational level, emitting a photon in the infrared. This photon carries energy away from the gas cloud, cooling it. This process is much more efficient than atomic cooling at the temperatures and densities typical of primordial gas clouds. It allows the gas to cool from thousands of Kelvin down to a few hundred Kelvin, which is cold enough for the gas to continue collapsing under gravity. But there's a catch. Molecular hydrogen has to form first, and forming H2 in the primordial universe wasn't easy. Bertrand. The formation of molecular hydrogen. In the modern universe, H2 forms easily on the surfaces of dust grains, tiny solid particles made of elements like carbon, silicon, and iron. When two hydrogen atoms land on a dust grain, they can meet and bond together, forming H2. The dust grain acts as a catalyst, facilitating the reaction. But in the primordial universe, there were no dust grains. There were no heavy elements to make dust from. So H2 had to form through gas phase reactions, reactions that occur when atoms and molecules collide in the gas without any solid surface to help. The main pathway for H2 formation in the primordial universe involves a negatively charged hydrogen ion called H-, H-. Here's how it works. 1. A hydrogen atom, H, captures a free electron, forming He. This requires a three-body collision, the hydrogen atom, the electron, and a third particle, usually another hydrogen atom, to carry away the excess energy. 2. The H ion then collides with another hydrogen atom, forming H2 and releasing the extra electron. This process is slow and inefficient, but it's faster in denser gas. As gas clouds became denser during the Dark Ages, the rate of H2 formation increased. There's also a secondary pathway involving H2+, a hydrogen molecule that's lost an electron. 1. Two hydrogen atoms collide at high speed, forming H2+ and releasing an electron. 2. The H2+ ion then captures an electron, forming H2. This pathway is even less efficient than the H pathway, but it contributes to the overall H2 formation rate. The key point is that H2 formation was a bottleneck in the process of forming the first stars. Gas clouds had to become dense enough for H2 to form at a significant rate. Only then could the gas cool efficiently and continue collapsing. This created a threshold effect. Gas clouds below a certain density couldn't form enough H2 to cool efficiently, so they couldn't collapse to form stars. But gas clouds above this density threshold could form H2, cool efficiently, and continue collapsing. The first stars formed in the gas clouds that crossed this threshold first, the densest concentrations of gas in the early universe. The Jeans mass. How big must a star-forming cloud be? Not every gas cloud can collapse to form a star. For a cloud to collapse under its own gravity, it must be massive enough that gravity overcomes the pressure from the hot gas. The minimum mass required is called the Jeans mass, and it depends on the temperature and density of the gas. The formula for the Jeans mass, derived by physicist James Jeans in 1902, is m-Jeans T3-R12, where T is the temperature and R is the density. This tells us that hotter gas has a higher Jeans mass because higher temperature means higher pressure, which resists collapse. Denser gas has a lower Jeans mass because higher density means stronger gravity. In the primordial universe, even after cooling by molecular hydrogen, the gas was relatively hot, a few hundred Kelvin compared to about 10 Kelvin for modern star-forming clouds. This meant the Jeans mass was high. Computer simulations suggest that the first star-forming clouds had masses of about 1005 to 10 Marek solar masses. That's 100 to 1,000 times the mass of our Sun. These were enormous clouds, much larger than typical star-forming clouds in the modern universe. But here's an important point. The Jeans mass tells us the minimum mass of the cloud that can collapse, not the mass of the star that will eventually form. When a massive cloud collapses, it doesn't all turn into a single star. Instead, the cloud fragments, breaking up into smaller pieces, each of which can potentially form a star. The question of how much fragmentation occurred in primordial star-forming clouds is one of the key uncertainties in understanding the first stars. Did these massive clouds fragment into many smaller stars, or did they form just a few very massive stars? The answer depends on the details of the cooling and collapse process, which we're still working to understand fully. The growth of structure, a hierarchical process. During the Dark Ages, structure didn't form all at once. Instead, it grew hierarchically, with small structures forming first and then merging to form larger structures. This hierarchical growth is a natural consequence of how gravity works. Small density fluctuations grow first because they have shorter dynamical timescales, the time it takes for gravity to pull matter together. Larger fluctuations take longer to grow because the matter has to fall over larger distances. So the first structures to form were small, dark matter halos, with masses perhaps 1,000,000 times the mass of the Sun. These halos formed early in the Dark Ages when the universe was only a few tens of millions of years old. As time went on, these small halos merged together, forming larger halos, and gas flowed into these halos, collecting in their centers. The first stars formed in the most massive halos that had formed by the end of the Dark Ages, halos with masses of about 10⁻⁶ solar masses. These halos had deep enough gravitational wells to attract and retain significant amounts of gas, and the gas in their centers became dense enough to form molecular hydrogen and cool efficiently. But not all halos formed stars at the same time. Star formation occurred first in the most massive halos, then gradually spread to less massive halos as the universe evolved. This is why we talk about the epoch of cosmic dawn, rather than a single moment when the first stars formed. It was a gradual process, occurring over perhaps 100 million years. The cosmic timeline. During the Dark Ages. Let's trace the timeline of the Dark Ages in more detail, understanding what was happening at different times. 380,000 years after the Big Bang, recombination. The universe becomes transparent. The cosmic microwave background is released. The temperature is about 3,000 Kelvin. Ordinary matter begins to respond to gravity without interference from radiation pressure. 1 million years, early Dark Ages. The universe has cooled to about 100 Kelvin. Dark matter halos are beginning to form. The cosmic web structure is starting to emerge. Ordinary matter is beginning to flow into dark matter halos. 10 million years, mid-Dark Ages. The universe has cooled to about 30 Kelvin. Significant dark matter halos have formed, with masses up to about 10⁵ solar masses. Gas is collecting in the centers of these halos. The first traces of molecular hydrogen are forming in the densest regions. 50 million years, late Dark Ages. The universe has cooled to about 20 Kelvin. The most massive halos have reached masses of about 10⁻⁶ solar masses. Gas in the centers of these halos has become dense enough for significant H2 formation. The gas is cooling efficiently and beginning to collapse. 200 million years, end of the Dark Ages. The first stars ignite, ending the Dark Ages. The universe is about to undergo a dramatic transformation. This timeline is approximate. The exact timing depends on the details of the cosmological model and the properties of dark matter. But it gives us a sense of the timescales involved. The Dark Ages lasted for about 100 to 200 million years, a brief period by cosmic standards, but long enough for gravity to work its magic and set the stage for the formation of the first stars. The role of streaming velocities. There's a subtle effect that influenced where the first stars formed, and it has to do with the relative motion between ordinary matter and dark matter in the early universe. Before recombination, ordinary matter was tightly coupled to photons through electromagnetic interactions. When photons moved, they dragged the ordinary matter with them. But dark matter doesn't interact with photons, so it wasn't affected by this coupling. The photons in the early universe weren't perfectly still. They had small-scale motions due to acoustic oscillations, sound waves, in the primordial plasma. These oscillations dragged ordinary matter back and forth, but left dark matter unaffected. At recombination, when ordinary matter decoupled from photons, it was left with a residual velocity relative to dark matter. This relative velocity, called the streaming velocity, was typically about 30 kilometers per second. This might not sound like much, but it had important consequences. In regions where ordinary matter was streaming rapidly relative to dark matter, it was harder for the ordinary matter to fall into dark matter halos. The streaming motion carried the gas past the halos before gravity could capture it. This meant that the first stars formed preferentially in regions where the streaming velocity was low, regions where ordinary matter and dark matter were moving together, allowing the gas to fall efficiently into dark matter halos. This effect is subtle, but it influenced the distribution of the first stars. It meant that star formation was slightly suppressed in some regions and enhanced in others, depending on the local streaming velocity. Turbulence and magnetic fields. As gas flowed into dark matter halos during the Dark Ages, it didn't fall smoothly. Instead, the infall was turbulent, with eddies and vortices forming in the gas. This turbulence was generated by several processes: the merging of dark matter halos, which sent shockwaves through the gas; the infall of gas along filaments, which created streams that collided and mixed; gravitational instabilities in the gas itself, which created density fluctuations. Turbulence is important because it can affect the fragmentation of gas clouds. Turbulent motions can provide additional support against gravitational collapse, increasing the gene's mass and potentially reducing fragmentation. Or turbulence can create local density enhancements that become sites of star formation. Understanding the role of turbulence in the formation of the first stars is an active area of research, with scientists using sophisticated computer simulations to model the turbulent flows in primordial gas clouds. There's also the question of magnetic fields. In the modern universe, magnetic fields play an important role in star formation, providing support against gravitational collapse and influencing the angular momentum of collapsing clouds. But did magnetic fields exist in the primordial universe? If so, where did they come from? There are several possibilities. Magnetic fields might have been generated during inflation or the Big Bang itself, creating a primordial magnetic field. Magnetic fields might have been generated by the motion of charged particles in the early universe through a process called the Biermann battery. Magnetic fields might have been generated by turbulent motions in the gas through a dynamo process. The strength and structure of any primordial magnetic fields are highly uncertain. They were probably very weak compared to magnetic fields in the modern universe. But even weak magnetic fields could have influenced the formation of the first stars, particularly if they were amplified by the collapse of gas clouds. This is another area of active research, with scientists working to understand the origin and evolution of magnetic fields in the early universe. The chemistry of the Dark Ages. Even though the primordial universe had very simple chemistry, just hydrogen, helium, and lithium, there were still some interesting chemical reactions occurring during the Dark Ages. We've already discussed the formation of molecular hydrogen, He2, which was crucial for cooling. But there were other molecules that formed as well. HD, deuterium hydride. This is a molecule consisting of one hydrogen atom and one deuterium atom, heavy hydrogen. It forms through reactions similar to those that form H2, but it's much rarer because deuterium is much less abundant than hydrogen. HD can cool gas even more efficiently than H2 at low temperatures, so it might have played a role in the formation of the first stars. LiH, lithium hydride. This is a molecule consisting of one lithium atom and one hydrogen atom. It's extremely rare because lithium is extremely rare in the primordial universe. But it's interesting from a theoretical perspective because it could potentially be detected through its absorption of light from distant quasars, providing a probe of the chemistry of the early universe. H2 plus and H3 plus, hydrogen molecular ions. These are ions formed when H2 gains or loses electrons or when H2 reacts with protons. They're important intermediaries in the chemistry of the early universe, participating in reactions that form and destroy H2. H plus, helium hydride ion. This is an ion consisting of one helium atom and one hydrogen atom. It was actually the first molecule to form in the universe, appearing even before H2. It forms when helium ions, H+, react with hydrogen atoms. He H+ was recently detected in a planetary nebula in our galaxy, confirming that it can form in astrophysical environments. These molecules were all present in trace amounts during the Dark Ages, and they participated in a complex network of chemical reactions. Understanding this chemistry is important for modeling the cooling and collapse of primordial gas clouds. The end of the Dark Ages approaches. As the Dark Ages progressed, conditions in the densest gas clouds were approaching the threshold for star formation. Let's imagine what was happening in one of these clouds. The cloud is located at the center of a dark matter halo, with a mass of about 1 million solar masses. Gas has been flowing into this halo for tens of millions of years, collecting in the center and forming a dense core. The gas in this core has a density of about 10 MeV 4 particles per cubic centimeter, much denser than the average density of the universe at this time, but still incredibly diffuse by terrestrial standards. For comparison, the air you're breathing has a density of about 1019 particles per cubic centimeter. The temperature of the gas is about 200–300 Kelvin, having cooled from thousands of Kelvin through the action of molecular hydrogen. This is still quite warm by human standards, about the temperature of a hot summer day, but it's cold enough for gravity to overcome the pressure and continue pulling the gas together. The cloud is slowly contracting under its own gravity. As it contracts, it becomes denser and hotter. But the molecular hydrogen continues to cool it, radiating away the heat generated by gravitational compression. The cloud is also rotating, slowly spinning due to the angular momentum it acquired as gas flowed into it along the filaments of the cosmic web. This rotation will play an important role in the final stages of collapse, potentially causing the cloud to flatten into a disk. As the cloud contracts, it reaches a critical point where it becomes unstable to fragmentation. The cloud breaks up into smaller pieces, each of which continues to collapse independently. One of these fragments is destined to become the first star. It's more massive than the others, perhaps 100 and 200 solar masses, and it's located near the center of the original cloud, where the density is highest. This fragment continues to collapse, becoming denser and hotter. The molecular hydrogen continues to cool it, but the cooling is becoming less efficient as the density increases. The temperature begins to rise. At the center of the E fragment, the density reaches 1010 particles per cubic centimeter, and the temperature reaches 1000 Kelvin. The gas is becoming opaque. Photons can no longer escape freely, so the cooling becomes less efficient. The collapse accelerates. The central density and temperature rise rapidly. The fragment is approaching the threshold for nuclear fusion. And then, after hundreds of millions of years of waiting, after the patient work of gravity pulling matter together, after the slow accumulation of gas in dark matter halos, after the formation of molecular hydrogen and the cooling of gas clouds, after the fragmentation and collapse of the cloud, the first star ignites. But before we witness that moment, we need to understand one more piece of the puzzle: the quantum fluctuations that started it all. In the next chapter, we'll explore how tiny variations in the fabric of space-time, born in the first moments of the universe, grew into the seeds of cosmic structure. We'll see how the universe went from nearly perfect uniformity to the rich tapestry of structure we see today. The Dark Ages were a time of preparation, a time when the universe was transforming itself from simple to complex. And at the end of this transformation, the first stars would shine, ending the darkness and beginning a new chapter in cosmic history. The quantum origin of cosmic structure. Every galaxy, every star, every planet, everything we see in the universe today can trace its origins back to quantum fluctuations that occurred in the first fraction of a second after the Big Bang. This is one of the most remarkable insights of modern cosmology. The largest structures in the universe began as the smallest possible fluctuations, quantum jitters in the fabric of space-time itself. To understand how the first stars formed, we need to understand these quantum seeds. We need to see how something that began at the scale of subatomic particles grew to the scale of galaxies and beyond. We need to trace the connection between the quantum realm and the cosmic realm, between the infinitesimally small and the incomprehensibly large. This is the story of how tiny seeds grew into cosmic structure. This is the story of how quantum uncertainty became cosmic destiny. Quantum fluctuations, the uncertainty principle in action. Let's begin with one of the fundamental principles of quantum mechanics, Heisenberg's uncertainty principle. This principle tells us that certain pairs of properties cannot both be precisely known at the same time. The more precisely you know one property, the less precisely you can know the other. The most famous example involves position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. But there's another pair of properties that's crucial for our story: energy and time. The energy-time uncertainty principle tells us that over very short time intervals, Energy can fluctuate by large amounts without violating the laws of physics. These fluctuations are called quantum fluctuations, and they're happening all around us, all the time, at the quantum scale. In empty space, what we might think of as a perfect vacuum, quantum fluctuations are constantly creating and destroying pairs of particles. These virtual particles pop into existence, exist for a brief moment, and then annihilate each other, disappearing back into the vacuum. This might sound like science fiction, but it's a real phenomenon that's been confirmed by experiments. Now, here's where it gets interesting for cosmology. In the early universe, during the inflationary epoch, these quantum fluctuations were stretched to cosmic scales. Fluctuations that began smaller than an atom were expanded to sizes larger than galaxies. And instead of disappearing back into the vacuum, they became frozen into the fabric of space itself. These stretched quantum fluctuations became the seeds of cosmic structure, the tiny variations in density that would eventually grow into galaxies, stars, and planets. Inflation, the great amplifier. We introduced inflation in Chapter 2, but let's revisit it now with a focus on how it amplified quantum fluctuations. Inflation was a period of exponential expansion that occurred in the first fraction of a second after the Big Bang. During this time, the universe grew by a factor of at least 10^26. That's 1, followed by 26 zeros. To put this in perspective, if an atom expanded by the same factor, it would become larger than the observable universe. This expansion happened incredibly fast. In about 10^32 seconds, the universe grew from smaller than a proton to roughly the size of a grapefruit. And it's this rapid expansion that's key to understanding how quantum fluctuations became cosmic seeds. Imagine a quantum fluctuation occurring in the early universe, a tiny region where the energy density is slightly higher or lower than average. In normal circumstances, this fluctuation would exist for only a brief moment before disappearing back into the vacuum. But during inflation, the universe is expanding so rapidly that the fluctuation gets stretched before it can disappear. The region of higher or lower energy density grows larger and larger, faster than the speed of light. This doesn't violate relativity because it's space itself that's expanding, not matter moving through space. Eventually, the fluctuation is stretched to a size larger than the horizon, the maximum distance that light can travel in the age of the universe at that time. Once a fluctuation is larger than the horizon, it becomes frozen. It can no longer evolve dynamically because different parts of it can't communicate with each other, since they're separated by more than light can travel. These frozen fluctuations became permanent features of the universe. When inflation ended, they remained as variations in the density of matter and energy, regions that were slightly denser or less dense than average. The power spectrum, the fingerprint of inflation. The quantum fluctuations that occurred during inflation weren't all the same size. There was a whole spectrum of fluctuations, ranging from very small scales to very large scales. The distribution of these fluctuations, how much variation there was at each scale, is called the power spectrum. The power spectrum is incredibly important because it's a fingerprint of the inflationary process. Different models of inflation predict different power spectra, so by measuring the power spectrum, we can test our theories about what happened during inflation. Remarkably, we can measure the power spectrum by observing the cosmic microwave background radiation. The tiny temperature variations we see in the CMB, those 1 part in 100,000 fluctuations we keep mentioning, directly reflect the density variations that existed at the time of recombination. And those density variations, in turn, reflect the quantum fluctuations that were generated during inflation. When we measure the CMB power spectrum, we find something remarkable. It's almost scale invariant, meaning that the amount of variation is roughly the same at all scales. This is exactly what the simplest models of inflation predict, providing strong evidence that inflation actually occurred. But the power spectrum isn't perfectly scale invariant. There are small deviations from perfect scale invariance. These deviations tell us about the details of the inflationary process, about how the expansion rate changed during inflation, and about the properties of the field that drove inflation. For our story, the key point is this. The power spectrum tells us where the first stars would eventually form. Regions with higher than average density would be the first to collapse under gravity, forming the first dark matter halos and eventually the first stars. From quantum to classical, the transition. There's something deeply mysterious about how quantum fluctuations became classical density variations. In quantum mechanics, particles exist in superpositions. They can be in multiple states at once until they're measured. But the density variations we see in the universe are classical. They have definite values, not superpositions. How did this transition from quantum to classical occur? This is one of the deep questions in cosmology, touching on the foundations of quantum mechanics itself. The most common explanation involves a process called decoherence. As quantum fluctuations were stretched during inflation, they became entangled with their environment, the surrounding space-time and matter fields. This entanglement caused the quantum superpositions to collapse into definite classical states. Another way to think about it, once a fluctuation was stretched beyond the horizon, it became impossible to perform any measurement that could detect its quantum nature. It became, for all practical purposes, classical. This transition from quantum to classical is crucial for our story, because it means the density variations that seeded cosmic structure were real, definite variations, not quantum superpositions. They were regions that were definitely denser or less dense than average, and they would remain so as the universe evolved. The growth of perturbations. Once inflation ended and the quantum fluctuations had become classical density variations, these variations began to evolve under the influence of gravity and other forces. This evolution is described by a set of equations called the perturbation equations, which track how small deviations from perfect uniformity grow or decay over time. The evolution of density perturbations depends on several factors. The scale of the perturbation. Small-scale perturbations covering small regions of space evolve differently from large-scale perturbations covering large regions. The composition of the universe. Perturbations in dark matter evolve differently from perturbations in ordinary matter, which evolve differently from perturbations in radiation. The epoch. Perturbations evolve differently during the radiation-dominated era, before recombination, than during the matter-dominated era, after recombination. Let's trace the evolution of a typical density perturbation from inflation to the formation of the first stars. During inflation. The perturbation is generated as a quantum fluctuation and stretched to cosmic scales. It becomes frozen when it crosses outside the horizon. After inflation, before horizon re-entry. The perturbation remains frozen because it's larger than the horizon. It can't evolve because different parts of it can't communicate. Horizon re-entry. As the universe expands, the horizon grows. Eventually, the horizon becomes larger than the perturbation, and the perturbation re-enters the horizon. Now it can begin to evolve dynamically. Radiation-dominated era. During this era, from the end of inflation to recombination, radiation dominates the energy density of the universe. Perturbations in ordinary matter want to grow under gravity, but they're prevented from doing so by radiation pressure. The photons push back against the matter, creating acoustic oscillations, sound waves in the primordial plasma. Recombination. When the universe becomes transparent, matter decouples from radiation. The radiation pressure disappears and matter perturbations can finally begin to grow freely under gravity. Matter-dominated era. After recombination, matter dominates the energy density of the universe. Perturbations in both dark matter and ordinary matter grow steadily under gravity. The growth is slow at first, but accelerates as perturbations become denser. Nonlinear growth. Eventually, the densest perturbations become so dense that the linear perturbation equations no longer apply. The perturbations enter the nonlinear regime, where gravity causes runaway collapse. This is when dark matter halos form, and eventually, when the first stars ignite. Dark matter versus ordinary matter, a tale of two perturbations. One of the key insights of modern cosmology is that dark matter and ordinary matter evolved very differently in the early universe, and this difference was crucial for the formation of the first stars. Dark matter doesn't interact with photons. It doesn't emit, absorb, or scatter light. This means that even before recombination, dark matter perturbations could grow under gravity without interference from radiation pressure. Ordinary matter, on the other hand, was tightly coupled to photons before recombination. The photons exerted pressure on the matter, preventing it from clumping together. This created a fundamental difference in how dark matter and ordinary matter evolved. Dark matter perturbations. These began growing as soon as they re-entered the horizon. By the time of recombination, dark matter perturbations had grown significantly, creating substantial variations in the dark matter density. Ordinary matter perturbations. These couldn't grow before recombination due to radiation pressure. They oscillated as sound waves in the primordial plasma, but they didn't grow. Only after recombination could they begin to grow under gravity. This means that by the time of recombination, the universe already had significant structure in its dark matter distribution, but the ordinary matter was still relatively smooth. The dark matter had created a gravitational scaffolding, a framework of halos and filaments into which ordinary matter could flow after recombination. This is why dark matter is so important for the formation of the first stars. Without dark matter, ordinary matter would have taken much longer to clump together and form stars. The universe might have remained dark for billions of years instead of hundreds of millions of years. Acoustic oscillations, the sound of the early universe. Before recombination, the universe was filled with sound waves, acoustic oscillations in the primordial plasma. These sound waves were created by the competition between gravity, which tried to pull matter together, and radiation pressure, which pushed matter apart. Here's how it worked. Imagine a region that's slightly denser than average. Gravity tries to pull more matter into this region, making it even denser. But as matter flows in, it compresses the photons in the region, increasing the radiation pressure. This pressure pushes back, driving matter out of the region. The matter overshoots, creating a region that's now less dense than average. Gravity then pulls matter back in, and the cycle repeats. This creates an oscillation, a sound wave propagating through the plasma. These acoustic oscillations left an imprint on the cosmic microwave background that we can still observe today. When we look at the CMB, we see a tau pattern of hot and cold spots that corresponds to the peaks and troughs of these ancient sound waves. The pattern is remarkably regular, with a characteristic scale corresponding to the distance sound could travel in the time between the Big Bang and recombination. This scale, called the sound horizon, is about 150 megaparsecs, about 500 million light-years in today's universe. The acoustic oscillations also affected the distribution of ordinary matter at recombination. Matter was concentrated in the regions where the sound waves had compressed it, creating a pattern of overdense and underdense regions. This pattern, called baryon acoustic oscillations, BAOs, is still visible in the distribution of galaxies today, providing another window into the early universe. For our story, the key point is that these acoustic oscillations created additional structure in the distribution of ordinary matter. When ordinary matter finally decoupled from radiation at recombination, it didn't have a perfectly smooth distribution. It already had variations imprinted by the acoustic oscillations. These variations influenced where the first stars would eventually form. The transfer function. From initial conditions to final structure, the relationship between the initial density perturbations, generated during inflation, and the final distribution of matter at any later time, is described by something called the transfer function. This function tells us how perturbations at different scales are amplified or suppressed as the universe evolves. The transfer function depends on the composition of the universe, particularly the relative amounts of dark matter, ordinary matter, and radiation. It also depends on the expansion history of the universe. One of the key features of the transfer function is that it suppresses small-scale perturbations in ordinary matter. This is because of the acoustic oscillations we just discussed. Small-scale perturbations in ordinary matter oscillated rapidly before recombination, and some of them were caught in a trough, a rarefaction phase, at recombination, making them less dense than they would have been otherwise. This suppression of small-scale perturbations in ordinary matter has important consequences for the formation of the first stars. It means that the smallest dark matter halos, those with masses below about 10 or 5 solar masses, had difficulty attracting ordinary matter. The ordinary matter density in these halos was suppressed by the acoustic oscillations. This created a characteristic minimum mass for the first star-forming halos, about 10 or 6 solar masses. Halos smaller than this couldn't attract enough ordinary matter to form stars. Only the most massive halos, where the gravitational pull was strong enough to overcome the suppression, could accumulate enough gas to form the first stars. Biasing. Why stars don't form everywhere. If the universe started with density variations that were almost perfectly uniform on large scales, only one part in 100,000 different from place to place, why don't we see stars and galaxies distributed uniformly throughout the universe? Why are there dense clusters of galaxies separated by vast voids containing very few galaxies? The answer has to do with a process called biasing. Stars and galaxies don't form everywhere. They form preferentially in the densest regions. This creates a bias in the distribution of luminous matter compared to the distribution of total matter. Here's how it works. For a gas cloud to collapse and form stars, it must exceed a certain density threshold. Regions that are only slightly denser than average won't form stars. They're not dense enough. Only regions that are significantly denser than average will form stars. This creates a nonlinear relationship between the density of matter and the density of stars. A small increase in matter density can lead to a large increase in star formation, while regions that are only slightly less dense than average might form no stars at all. This biasing effect was even more pronounced for the first stars. Because the cooling was less efficient in the primordial universe, the density threshold for star formation was higher. Only the very densest regions, the peaks of the density distribution, could form stars. This means the first stars formed in a highly biased distribution. They didn't form uniformly throughout the universe, but only in the densest nodes of the cosmic web, the places where multiple filaments intersected, where dark matter halos were most massive, where gas could accumulate most efficiently. If we could make a map of the universe at the end of the Dark Ages, showing where the first stars were forming, we'd see a pattern of bright points scattered throughout space, concentrated along filaments and at the intersections of filaments, with vast dark voids between them. This pattern would reflect the underlying cosmic web structure, but amplified by the biasing effect. The role of angular momentum. As gas flowed into dark matter halos during the Dark Ages, it didn't fall straight in. Instead, it had angular momentum. It was rotating. This rotation was a consequence of the tidal torques exerted by the surrounding matter distribution. Here's how tidal torques work. Imagine a proto-halo, a region that will eventually collapse to form a dark matter halo. This proto-halo is surrounded by other overdense regions, distributed asymmetrically around it. The gravitational pull from these surrounding regions isn't uniform. It's stronger on one side than the other. This asymmetric gravitational pull exerts a torque on the proto-halo, causing it to spin. The amount of spin depends on the distribution of matter around the proto-halo and the shape of the proto-halo itself. By the time the halo has collapsed and gas has begun flowing into it, the gas has acquired significant angular momentum. This angular momentum has important consequences for star formation. Disk formation. As gas with angular momentum falls into the halo, it can't fall straight to the center. Instead, it settles into a rotating disk, similar to the disk of a spiral galaxy or the disk from which planets form around stars. Fragmentation. The rotating disk can fragment into multiple pieces, each of which might form a star. This could lead to the formation of binary or multiple star systems rather than single isolated stars. Spin-up. As gas collapses toward the center of the halo, conservation of angular momentum causes it to spin faster, like a figure skater pulling in their arms. This spin-up can provide additional support against gravitational collapse, potentially affecting the mass of the stars that form. Understanding the role of angular momentum in the formation of the first stars is an active area of research. Computer simulations show that the gas does indeed form rotating disks, and these disks can fragment, potentially forming multiple stars. But the details depend on many factors, including the cooling rate, the turbulence in the gas, and the strength of any magnetic fields. Number are feedback, how the first stars affected their environment. Once the first stars began to form, they didn't just passively exist, they actively affected their environment. This is called feedback, and it's one of the most important processes in galaxy formation and evolution. The first stars would have produced feedback through several mechanisms. Radiation. The first stars were incredibly luminous, producing copious amounts of ultraviolet radiation. This radiation could ionize the surrounding gas, heating it and preventing it from cooling and forming more stars. Stellar winds. Massive stars produce powerful stellar winds, streams of particles flowing out from the star's surface. These winds could push gas out of the star-forming region, again preventing further star formation. Supernovae. When the first stars died, they exploded as supernovae, releasing enormous amounts of energy. These explosions could blow gas out of the dark matter halos, enriching the surrounding intergalactic medium with heavy elements and potentially triggering or suppressing star formation in nearby regions. This feedback created a complex interplay between star formation and the environment. The first stars changed the conditions in which subsequent stars would form, creating a feedback loop that regulated the overall rate of star formation. In some regions, feedback might have been negative. The first stars prevented further star formation by heating or expelling the gas. In other regions, feedback might have been positive. Supernova shock waves compressed nearby gas clouds, triggering new episodes of star formation. Understanding this feedback is crucial for understanding how the universe evolved from the first stars to the galaxies we see today. It's a key piece of the puzzle that scientists are still working to fully understand. The cosmic variance. Why every region is different. When we talk about the formation of the first stars, we're describing a statistical process. Not every region of the universe evolved in exactly the same way. Some regions formed stars earlier, some later. Some formed many stars, some formed few. This variation is called cosmic variance, and it's a natural consequence of the random nature of the initial density perturbations. Remember, the density perturbations were generated by quantum fluctuations during inflation. These fluctuations were random. There was no pattern or design to them. They were simply the result of quantum uncertainty amplified to cosmic scales. This randomness means that different regions of the universe had different initial conditions. Some regions happened to have higher than average density, while others had lower than average density. These differences were small initially, only 1 part in 100,000, but they grew over time, eventually leading to significant differences in how different regions evolved. In regions where the initial density was slightly higher, dark matter halos formed earlier and grew larger. Gas flowed into these halos more efficiently, and the first stars formed sooner. These regions became the sites of vigorous star formation, eventually evolving into the dense galaxy clusters we see today. In regions where the initial density was slightly lower, structure formation proceeded more slowly. Dark matter halos formed later and remained smaller. Gas was less concentrated, and star formation was delayed. These regions became the voids we see in the large-scale structure of the universe today, vast regions containing very few galaxies. This cosmic variance means that when we talk about the first stars, we're really talking about a population of stars that formed over a range of times and in a variety of environments. There wasn't a single moment when the first star formed. Instead, there was a gradual transition from a universe with no stars to a universe with many stars, occurring over perhaps 100 million years. The observable consequences. The quantum fluctuations generated during inflation have left observable imprints on the universe that we can detect today. These observations provide powerful tests of our theories about the early universe and the formation of the first stars. The cosmic microwave background. The temperature variations in the CMB directly reflect the density variations at recombination, which in turn reflect the quantum fluctuations from inflation. By measuring the CMB in exquisite detail, we can reconstruct the initial conditions from which all cosmic structure grew. The large-scale structure. The distribution of galaxies in the universe today reflects the initial density perturbations filtered through billions of years of gravitational evolution. By mapping the positions of millions of galaxies, we can test our theories about how structure grows from initial perturbations. The Lyman alpha forest. When we observe distant quasars, we see absorption lines in their spectra caused by hydrogen gas along the line of sight. These absorption lines create a forest of features that encode information about the distribution of gas in the early universe. By analyzing this forest, we can learn about the density fluctuations and the thermal history of the intergalactic medium. Gravitational lensing. The gravity of dense structures bends light passing near them, creating distortions in the images of background galaxies. By measuring these distortions, we can map the distribution of matter, including dark matter, in the universe, testing our theories about structure formation. The first galaxies. With powerful telescopes like the James Webb Space Telescope, we can now observe galaxies that formed when the universe was only a few 100 million years old. These galaxies contain stars from the second or third generation after the very first stars, and their properties tell us about the conditions in which they formed. All of these observations are consistent with the picture we've developed. The universe started with tiny quantum fluctuations that were amplified during inflation, grew into density perturbations that evolved under gravity, and eventually collapsed to form the first stars and galaxies. From seeds to stars. We've traced the journey from quantum fluctuations to cosmic structure, from the smallest scales to the largest, from the earliest moments of the universe to the end of the Dark Ages. We've seen how tiny seeds planted during inflation grew into the structures that would eventually form the first stars. But we haven't yet witnessed the moment of formation itself, the moment when a collapsing gas cloud became dense and hot enough to ignite nuclear fusion. We haven't seen the first light. That's the story we'll tell in the next chapter. We'll watch as a gas cloud collapses under its own gravity, fragmenting and heating, approaching the critical threshold for star formation. We'll see how molecular hydrogen cools the gas, allowing it to continue collapsing. We'll witness the formation of a protostar, and finally, the ignition of nuclear fusion. We'll see the moment when the Dark Ages ended and the cosmic dawn began. But before we get there, let's appreciate what we've learned in this chapter. The largest structures in the universe, galaxies, galaxy clusters, the cosmic web, all began as quantum fluctuations smaller than an atom. These fluctuations were amplified during inflation, becoming frozen into the fabric of space. They evolved under gravity, growing from tiny variations into substantial density perturbations. They created the cosmic web of dark matter, into which ordinary matter flowed after recombination, and they determined where the first stars would form, in the densest nodes of this cosmic web, where gas could accumulate and cool efficiently. This is the story of how quantum uncertainty became cosmic destiny. This is the story of how the seeds of light were planted in the fabric of the universe, waiting to grow into the first stars. The moment approaches. We've journeyed through billions of years of cosmic history, from the Big Bang to the end of the Dark Ages. We've seen how the universe evolved from a hot, dense state to a cold, dark expanse of hydrogen and helium gas. We've watched as gravity slowly pulled matter together, creating the cosmic web of dark matter, halos, and filaments. We've understood how quantum fluctuations grew into the seeds of cosmic structure. Now, finally, we're ready to witness the formation of the first star. Imagine a dark matter halo located at a dense node in the cosmic web, about 150 million years after the Big Bang. This halo has a mass of about 1 million times the mass of our Sun, massive enough to attract and retain a significant amount of gas, but small enough that it formed relatively early in cosmic history. For tens of millions of years, gas has been flowing into this halo, collecting in its center. The gas has cooled through the action of molecular hydrogen, radiating away the heat generated by gravitational compression. The central density has been steadily increasing, approaching the critical threshold for star formation. Now, that threshold is about to be crossed. The gas cloud at the center of the halo is becoming unstable. Gravity is winning the battle against pressure. The cloud is beginning to collapse. This is the moment we've been waiting for. This is the first collapse. The conditions for collapse. Before we watch the collapse unfold, let's understand the conditions that make it possible. For a gas cloud to collapse and form a star, several requirements must be met. Sufficient mass. The cloud must exceed the Jeans mass, the minimum mass required for gravity to overcome pressure. In the primordial universe, this was about 1,000 to 10,000 solar masses, much larger than the Jeans mass for modern star-forming clouds. Efficient cooling. The cloud must be able to radiate away the heat generated by gravitational compression. Without efficient cooling, the temperature and pressure would rise, halting the collapse. Molecular hydrogen provides this cooling in the primordial universe. Low angular momentum. While some rotation is inevitable, too much angular momentum would prevent the gas from falling to the center. The gas would instead settle into a stable rotating disk without forming a star. Fortunately, the angular momentum of primordial gas clouds was typically low enough to allow collapse. Minimal turbulence. Strong turbulent motions could provide additional support against collapse, increasing the effective Jeans mass. The primordial gas clouds did have some turbulence generated by the infall of gas and the merging of dark matter halos, but it wasn't strong enough to prevent collapse in the densest regions. In our halo, all these conditions are met. The gas cloud at the center has a mass of about 2,000 solar masses, well above the Jeans mass. Molecular hydrogen has formed at a sufficient abundance to cool the gas efficiently. The angular momentum is moderate, allowing gas to fall toward the center while also creating some rotation. And while there's turbulence in the gas, it's not strong enough to prevent collapse. The stage is set. The collapse is about to begin. The onset of instability. The collapse doesn't begin suddenly. Instead, there's a gradual transition from a state of quasi-equilibrium, where gravity and pressure are nearly balanced, to a state of runaway collapse, where gravity dominates and the cloud contracts rapidly. This transition occurs when the cloud exceeds the Jeans mass. At this point, the gravitational force pulling the cloud together becomes stronger than the pressure force pushing it apart. The cloud becomes unstable to gravitational collapse, but the collapse doesn't happen uniformly throughout the cloud. Instead, it begins in the densest regions, the center of the cloud, where the gravitational pull is strongest. The central region starts to contract, becoming denser and pulling in more gas from the outer regions. As the central region contracts, it heats up due to gravitational compression. This heating would normally create pressure that resists further collapse. But the molecular hydrogen in the gas radiates away this heat, keeping the temperature relatively low and allowing the collapse to continue. This is a critical point. If the cooling weren't efficient enough, the collapse would stall. The temperature would rise, the pressure would increase, and the cloud would settle into a new equilibrium without forming a star. But in our cloud, the cooling is just efficient enough to allow the collapse to proceed. The central region continues to contract, becoming denser and denser. The density increases from 10^4 particles per cubic centimeter to 10^5, then 10^6, then 10^7. With each increase in density, the gravitational pull becomes stronger, accelerating the collapse. The collapse is entering the runaway phase. There's no turning back. Now, the free fall timescale. How fast does the collapse occur? The answer depends on the density of the gas. The time it takes for a gas cloud to collapse under its own gravity is called the free fall timescale, and it's given by TFF 1 GR, where G is the gravitational constant and R is the density. This formula tells us that denser gas collapses faster. The free fall time is inversely proportional to the square root of the density. At the beginning of the collapse, when the density is about 10 more 4 particles per cubic centimeter, the free fall time is about 10 million years. This might seem like a long time, but it's actually quite short by cosmic standards. It's less than 0.1% of the current age of the universe. As the collapse proceeds and the density increases, the free fall time decreases. When the density reaches 10 over 8 particles per cubic centimeter, the free fall time is only about 10,000 years. When the density reaches 10 to 12 particles per cubic centimeter, the free fall time is only about 1 year. This accelerating collapse is one of the characteristic features of gravitational instability. The collapse starts slowly, but speeds up as it proceeds, eventually becoming extremely rapid in the final stages. For our collapsing cloud, the total time from the onset of instability to the formation of a protostar is only about 100,000 to 1 million years, a blink of an eye in cosmic time. Fragmentation. One cloud, many stars. As the cloud collapses, an important question arises. Will it form a single massive star, or will it fragment into multiple smaller stars? Fragmentation occurs when a collapsing cloud becomes unstable to the formation of substructure. Instead of collapsing as a single unit, the cloud breaks up into smaller pieces, each of which collapses independently. Whether fragmentation occurs depends on the balance between several competing effects. Gravity. This promotes fragmentation by amplifying density variations. If one region of the cloud is slightly denser than average, gravity will pull more gas into that region, making it even denser and potentially causing it to separate from the rest of the cloud. Pressure. This resists fragmentation by smoothing out density variations. If the gas is hot and has high pressure, pressure gradients will push gas from high-density regions to low-density regions, preventing fragmentation. Cooling. This promotes fragmentation by reducing the pressure. If the gas can cool efficiently, the pressure decreases, making it easier for gravity to create separate dense clumps. Turbulence. This can either promote or resist fragmentation, depending on its properties. Turbulent motions can create density variations that become sites of fragmentation, but they can also provide support against collapse, preventing fragmentation. In modern star-forming clouds, fragmentation is very common. A single molecular cloud can fragment into hundreds or thousands of smaller clumps, each forming a star. This is why stars typically form in clusters rather than in isolation. But in the primordial universe, fragmentation was less efficient. The cooling was less effective than in modern clouds, which meant the gas remained hotter and the pressure was higher. This higher pressure resisted fragmentation, favoring the formation of fewer, more massive stars. Computer simulations of primordial star formation show that fragmentation does occur, but it's limited. A typical primordial cloud might fragment into a few pieces, perhaps 2 to 10, rather than hundreds or thousands. Each fragment would then collapse to form a massive star with a mass of 100 to 1,000 solar masses. In our cloud, let's imagine that fragmentation produces 3 main fragments. The largest fragment, located at the very center of the cloud, has a mass of about 200 solar masses. 2 smaller fragments, located slightly off-center, have masses of about 100 solar masses each. These 3 fragments will each collapse to form a star, creating a small multiple star system, the first stellar system in the universe. Nador? The role of rotation. As the cloud collapses, its rotation becomes increasingly important. The cloud started with some angular momentum, acquired through tidal torques from the surrounding matter distribution. As the cloud contracts, conservation of angular momentum causes it to spin faster, like a figure skater pulling in their arms. This spin-up has important consequences for the collapse. The rotation creates a centrifugal force that opposes gravity in the direction perpendicular to the rotation axis. This causes the cloud to flatten into a disk shape, with the rotation axis as the disk's axis. The disk formation is a crucial step in the collapse process. In the direction parallel to the rotation axis, the gas can continue to fall freely toward the center. But in the direction perpendicular to the rotation axis, the centrifugal force prevents the gas from falling directly to the center. Instead, the gas settles into a rotating disk. This disk is similar in some ways to the disks we see around young stars in the modern universe, the protoplanetary disks from which planets form. But there's an important difference. The primordial disks are much more massive. While a typical protoplanetary disk might have a mass of 0.01 solar masses, a primordial disk might have a mass of 10 to 100 solar masses. The disk doesn't remain stable. It's massive enough that it can become gravitationally unstable, developing spiral arms and clumps. These clumps can become the sites of fragmentation, potentially forming additional stars. In our collapsing cloud, the rotation causes the largest fragment to flatten into a disk with a radius of about 1,000 astronomical units, AU, about 25 times the size of our solar system. This disk is rotating rapidly with a rotation period of about 1,000 years. At the center of this disk, gas is still falling inward, accumulating in an increasingly dense core. This core will become the protostar, the precursor to the first star. The formation of the protostar. As gas continues to fall into the center of the disk, the central density and temperature increase. When the central density reaches about 1010 particles per cubic centimeter and the temperature reaches about 1000 Kelvin, something important happens. The gas becomes opaque to radiation. Up to this point, the gas has been transparent. Photons produced by molecular hydrogen cooling could escape freely, carrying energy away from the cloud. But at these high densities, the gas becomes opaque. Photons are absorbed and re-emitted many times before they can escape, effectively trapping the radiation inside the gas. This is called the opacity limit, and it marks a crucial transition in the collapse. Before the opacity limit, the gas could cool efficiently, and the temperature remained relatively low even as the density increased. After the opacity limit, the cooling becomes much less efficient, and the temperature begins to rise rapidly. This rising temperature creates pressure that slows the collapse. The gas at the center of the disk settles into a state of approximate equilibrium, where the pressure gradient balances gravity. This central object is called a protostar. The protostar is not yet a true star. It's not yet hot enough at its center to ignite nuclear fusion, but it's the seed from which a star will grow. As more gas falls onto the protostar from the surrounding disk, the protostar's mass increases, and as its mass increases, so does the temperature and pressure at its center. In our collapsing cloud, the protostar that forms at the center of the largest fragment has an initial mass of about 1 solar mass, much smaller than the final mass of the star it will become. But it's growing rapidly, accreting gas from the surrounding disk at a rate of about 0.01 solar masses per year. At this rate, the protostar will reach a mass of 100 solar masses in only 10,000 years, and long before that, it will become hot enough to ignite nuclear fusion, transforming from a protostar into a true star. The accretion disk. The disk surrounding the protostar is not static. Gas in the disk is constantly moving, spiraling inward toward the protostar. This inward motion is driven by a process called viscous transport. Here's how it works. The gas in the disk is rotating, with the inner regions rotating faster than the outer regions. This is called Keplerian rotation. Friction between adjacent regions of gas, caused by turbulence, magnetic fields, or other processes, transfers angular momentum outward. As the inner gas loses angular momentum, it spirals inward. As the outer gas gains angular momentum, it moves outward. This creates a flow of gas from the outer disk to the inner disk and eventually onto the protostar. The rate of this flow, the accretion rate, determines how quickly the protostar grows. In modern protostellar disks, the accretion rate is typically very low, about 10^6 to 10^5 solar masses per year. At this rate, it takes millions of years for a solar mass star to form. But in primordial disks, the accretion rate is much higher, about 10 to the power 3 to 10 to the power 2 solar masses per year, roughly 1,000 times faster than in modern disks. This high accretion rate is due to the higher mass of the disk and the more efficient transport of angular momentum. This high accretion rate has important consequences. It means the first stars formed very quickly, in only tens of thousands of years rather than millions of years. It also means the first stars could grow to very large masses before nuclear fusion ignited, because the accretion was so rapid. As gas spirals inward through the disk, it releases gravitational potential energy. This energy heats the disk, making it glow. In modern protostellar disks, this glow is visible in the infrared. In primordial disks, the higher accretion rate produces more heating, making the disk even brighter. This glowing disk is one of the first sources of light in the universe, not starlight yet, but the warm glow of gravitational energy being converted to radiation. If we could observe our collapsing cloud at this stage, we'd see a faint infrared glow coming from the disk, growing brighter as the accretion rate increases. Stars, outflows, and jets. As the protostar accretes gas from the disk, it doesn't just grow passively. It also launches powerful outflows, streams of gas flowing away from the protostar at high speeds. These outflows are a ubiquitous feature of star formation in the modern universe. Nearly every young star has associated outflows, often taking the form of collimated jets, narrow beams of gas shooting out from the star's poles at speeds of hundreds of kilometers per second. The exact mechanism that launches these outflows is still not fully understood, but it's thought to involve magnetic fields. The rotating disk generates magnetic fields through a dynamo process. These magnetic fields become twisted by the rotation, creating a magnetic pressure that drives gas away from the disk. The outflows serve an important function. They carry away angular momentum from the system. Remember, the gas in the disk has angular momentum, and this angular momentum must be removed for the gas to fall onto the protostar. The viscous transport in the disk moves angular momentum outward, but the outflows provide an additional mechanism for removing angular momentum from the system entirely. In primordial star formation, outflows likely played a similar role. Computer simulations show that primordial protostars do launch outflows, though the properties of these outflows are somewhat different from modern outflows due to the different conditions. The primordial outflows were probably more massive and more powerful than modern outflows, reflecting the higher accretion rates in larger masses involved. They might have reached speeds of 20 kilometers per second or more, carrying away significant amounts of mass and energy. These outflows would have had important effects on the surrounding gas. They would have created cavities in the gas cloud, pushing gas away from the protostar. They might have triggered additional star formation by compressing nearby gas, and they would have been one of the first sources of mechanical feedback in the universe, the first example of stars affecting their environment. In our collapsing cloud, the protostar launches bipolar outflows, two jets shooting out from the north and south poles of the disk. These jets plow into the surrounding gas, creating shock waves and heating the gas. The jets are visible as faint glowing streams marking the location of the forming star. The approach to ignition. As the protostar continues to accrete gas, its mass increases, and as its mass increases, so does the temperature and pressure at its center. The protostar is approaching the critical threshold for nuclear fusion. Nuclear fusion is the process that powers stars. It occurs when atomic nuclei collide with enough energy to overcome their electrical repulsion and fuse together, forming heavier nuclei and releasing energy. In stars, the primary fusion reaction is the conversion of hydrogen into helium. But fusion requires extreme conditions. The nuclei must be moving fast enough to overcome their electrical repulsion, which means the temperature must be very high, at least 10 million Kelvin for hydrogen fusion, and the density must be high enough that collisions occur frequently, at least 1026 particles per cubic centimeter. As the protostar grows, the temperature and density at its center increase due to gravitational compression. When the protostar reaches a mass of about 0.08 solar masses, the central temperature reaches 10 million Kelvin, hot enough for hydrogen fusion to begin. But our protostar is growing much faster than this. By the time it reaches 0.08 solar masses, it's accreting gas so rapidly that it doesn't have time to settle into equilibrium. It keeps growing, reaching 1 solar mass, then 10 solar masses, then 100 solar masses. At some point during this rapid growth, the central temperature becomes high enough for fusion to ignite. The exact mass at which this occurs depends on the accretion rate and the structure of the protostar, but it's probably somewhere between 10 and 100 solar masses for the first stars. When fusion ignites, the protostar becomes a true star. It begins generating energy through nuclear reactions, not just through gravitational contraction. This marks a fundamental transition, the birth of the first star. But the star doesn't stop accreting gas immediately. The fusion energy is generated at the center of the star, and it takes time for this energy to reach the surface and create enough radiation pressure to halt the infall of gas. During this time, the star continues to grow, potentially reaching masses of several hundred solar masses. In our collapsing cloud, the protostar at the center of the largest fragment reaches a mass of about 50 solar masses before fusion ignites. At this point, the central temperature is about 15 million Kelvin, and the central density is about 1026 particles per cubic centimeter, conditions that are perfect for hydrogen fusion. The fusion reactions begin slowly at first, producing a trickle of energy, but they quickly accelerate, producing more and more energy as the temperature rises. Within a few years, the fusion reactions are producing enough energy to balance the energy radiated from the star's surface. The star has reached the main sequence, the long stable phase of stellar evolution, where fusion energy balances radiative losses. The first star has been born. The moment of first light. Let's pause and appreciate what has just happened. After hundreds of millions of years of darkness, after the patient work of gravity pulling matter together, after the slow accumulation of gas in dark matter, halos, after the formation of molecular hydrogen and the cooling of gas clouds, after the fragmentation and collapse of the cloud, after the formation of a protostar and its rapid growth through accretion, the first star has ignited. This is the moment of cosmic dawn. This is the end of the Dark Ages. This is the beginning of a new era in cosmic history. If we could observe this moment, what would we see? At first, not much. The star is still deeply embedded in the gas cloud from which it formed. The light from the star is absorbed by the surrounding gas and re-radiated at longer wavelengths. But the star is incredibly luminous, about 1 million times more luminous than our Sun. This enormous luminosity begins to heat the surrounding gas, ionizing it and creating a bubble of hot ionized gas around the star. The ionized gas is transparent to the star's light, so as the ionization front expands outward, more and more of the star's light can escape. The bubble grows, pushing aside the neutral gas, creating a cavity around the star. Within a few thousand years, the ionization front has expanded far enough that the star becomes visible from the outside. For the first time, starlight escapes into the universe. The Dark Ages are over. This first light is predominantly ultraviolet. The star is so hot, with a surface temperature of about 100,000 Kelvin, that most of its light is emitted at ultraviolet wavelengths. This ultraviolet light is energetic enough to ionize hydrogen atoms, splitting them into protons and electrons. As the ultraviolet light spreads outward from the star, it creates an expanding bubble of ionized gas. This bubble is called an HII region, pronounced H2 region, named after ionized hydrogen. The HII region glows with a characteristic red light, produced when electrons recombine with protons and cascade down through the energy levels of the hydrogen atom. This red glow is the signature of the first stars. It's the light that ended the Dark Ages and began the epoch of ionization, the period when the universe transitioned from neutral to ionized. Multiple stars, multiple lights. Remember, our gas cloud fragmented into 3 pieces, each forming a protostar. The largest fragment formed a star of about 200 solar masses after continuing to accrete gas after fusion ignited. The two smaller fragments formed stars of about 100 solar masses each. These three stars ignite at slightly different times, separated by perhaps a few thousand years. Each star creates its own HII region, and these regions eventually merge into a single large bubble of ionized gas. The three stars orbit each other, forming a gravitationally bound system, the first stellar system in the universe. The orbital periods are long, perhaps 10,000 to 100,000 years, because the stars are separated by large distances, thousands of AU. This multiple star system is probably typical of the first stars. Computer simulations suggest that fragmentation usually produces a few stars rather than a single isolated star. So the first stars probably formed in small groups, creating the first stellar systems. These systems would have been spectacular to observe. Three massive, incredibly luminous stars, each shining with the light of 1,000,000 suns, orbiting each other in a cosmic dance. Their combined light would have created a huge bubble of ionized gas, perhaps 100 light-years across, glowing with the red light of hydrogen recombination. This bubble would have been visible from vast distances if there were observers elsewhere in the universe at this time, and of course, there weren't. They could have seen this bubble from millions of light-years away, a beacon announcing the birth of the first stars. The impact on the surrounding gas. The formation of the first stars had immediate and profound effects on the surrounding gas. The ultraviolet radiation from the stars ionized the gas, heating it to about 10,000 Kelvin. This is much hotter than the gas was before. Remember, the gas in the Dark Ages had cooled to only about 20–30 Kelvin. This heating had important consequences. Hot gas has high pressure, which resists gravitational collapse. This means that the formation of the first stars actually suppressed further star formation in the immediate vicinity. The hot, ionized gas couldn't cool and collapse to form new stars. This is an example of negative feedback. The first stars prevented the formation of additional stars nearby. This feedback helped regulate the rate of star formation, preventing all the gas from turning into stars at once. But the feedback wasn't entirely negative. The ionizing radiation from the first stars could also trigger star formation in more distant regions. When the ionization front reached a nearby gas cloud, it compressed the cloud, potentially triggering its collapse and the formation of new stars. The stellar winds from the first stars also affected the surrounding gas. These winds, streams of particles flowing out from the stars' surfaces at speeds of thousands of kilometers per second, pushed gas away from the stars, creating cavities and shells. And we haven't even mentioned the most dramatic form of feedback yet, supernovae. When the first stars died, and they would die young, after only a few million years, they would explode as supernovae, releasing enormous amounts of energy and heavy elements. But that's a story for a later chapter. For now, let's appreciate what we've witnessed: the first collapse, the formation of the first protostar, the ignition of the first fusion reactions, and the emergence of the first light. The Dark Ages have ended. The cosmic dawn has begun. In the next chapter, we'll explore what these first stars were like, their properties, their structure, their evolution. We'll see how they differed from modern stars and why they were so important for the evolution of the universe. The first stars awaken. The universe has changed. After hundreds of millions of years of darkness, light has returned. The first stars have ignited, their nuclear furnaces burning bright, transforming hydrogen into helium and releasing enormous amounts of energy in the process. But what were these first stars like? How did they differ from the stars we see in the sky today? What made them special, and why do we call them titans? The answers to these questions reveal a universe very different from our own, a universe of extremes where stars were more massive, more luminous, and shorter-lived than almost any stars that exist today. These were the population 3 stars, the first generation of stars in the universe, and they were unlike anything that came after them. This chapter is about these cosmic titans, what they were, how they lived, and why they mattered. Population 3. The first-generation astronomers classify stars into different populations based on their chemical composition. Population 1 stars are metal-rich stars like our Sun. They contain significant amounts of elements heavier than helium, carbon, oxygen, nitrogen, iron, and so on. These stars formed relatively recently in cosmic history from gas that had been enriched by previous generations of stars. Our Sun is a population 1 star formed about 4.6 billion years ago from gas that contained about 2% heavy elements by mass. Population 2 stars are metal-poor stars that formed earlier in cosmic history. They contain much less heavy elements than population 1 stars, typically 0.1% to 0.1% heavy elements by mass. These stars are found in the oldest parts of galaxies, such as globular clusters and galactic halos. They formed from gas that had been only slightly enriched by earlier generations of stars. Population ethers stars are the hypothetical first generation of stars formed from primordial gas containing no heavy elements at all, just hydrogen, helium, and trace amounts of lithium. These stars have never been directly observed, but we're confident they existed because the universe had to start somewhere, and the first stars must have formed from the primordial gas created in the Big Bang. The naming convention is backwards. Population 3. Stars came first, not third, because astronomers discovered population 1 and 2 stars before they realized there must have been an even earlier generation. But the name has stuck, and we still call the first stars population 3. The key difference between population 3 stars and later generations is the absence of heavy elements. This might seem like a minor detail, but it had profound consequences for the properties of these stars. This were massive beyond measure. The most striking feature of population 3 stars was their mass. While modern stars range from about 0.08 solar masses, the minimum mass for hydrogen fusion, to about 100-150 solar masses, the maximum mass that can form without becoming unstable, population 3 stars were likely much more massive, perhaps 100 to 1,000 solar masses, with some possibly even larger. Why were they so massive? The answer has to do with cooling and fragmentation. In modern star-forming clouds, heavy elements like carbon and oxygen act as efficient coolants. They can radiate energy very effectively, allowing gas clouds to cool to very low temperatures, about 10 Kelvin. At these low temperatures, the gene's mass is small, and clouds can fragment into many small pieces, forming many low-mass stars. But in the primordial universe, there were no heavy elements. The only coolant available was molecular hydrogen, which is much less efficient than heavy elements. This meant primordial gas clouds could only cool to about 200 to 300 Kelvin, much warmer than modern star-forming clouds. With these higher temperatures, the gene's mass was larger and fragmentation was less efficient. Primordial clouds broke up into fewer, more massive fragments, each of which formed a more massive star. Computer simulations of primordial star formation consistently show this result. The first stars were massive, with typical masses of 100 to 300 solar masses. Some simulations produce stars as massive as 1,000 solar masses or more. These were true giants, titans among stars. To put this in perspective, the most massive star known in the modern universe, R136A1, has a mass of about 265 solar masses. The first stars might have been even more massive than this. Burning bright, the luminosity of giants. Massive stars are incredibly luminous. The luminosity of a star, the total amount of energy it radiates per second, scales roughly as the fourth power of its mass. This means a star that's 10 times more massive than the Sun is about 10,000 times more luminous. A star that's 100 times more massive is about 100 million times more luminous. The first stars, with masses of 100 to 300 solar masses, would have been extraordinarily luminous, about 1 million to 10 million times more luminous than the Sun. This is comparable to the luminosity of an entire small galaxy in the modern universe. This enormous luminosity had important consequences. It meant the first stars were incredibly hot at their surfaces, about 100,000 Kelvin, compared to 6,000 Kelvin for the Sun. At these temperatures, the stars emitted most of their light in the ultraviolet part of the spectrum. This ultraviolet light was energetic enough to ionize hydrogen atoms, splitting them into protons and electrons. Each first star created a large bubble of ionized gas around itself, an HEII region that could extend for hundreds of light years. The luminosity also meant the first stars exerted strong radiation pressure on their surroundings. Photons carry momentum, and when they're absorbed or scattered by gas, they transfer that momentum to the gas, pushing it away. For the most massive first stars, this radiation pressure was strong enough to blow away the surrounding gas, potentially halting further accretion and limiting the final mass of the star. This radiation pressure might explain why we don't see stars more massive than about 150–300 solar masses in the modern universe. Above this mass, the radiation pressure becomes so strong that it prevents further accretion, setting an upper limit on stellar mass. The first stars might have been able to exceed this limit because they formed so rapidly, accreting gas faster than radiation pressure could blow it away. The structure of a population 3 star. Let's imagine we could slice open a population 3 star and look inside. What would we see? At the center is the core, where nuclear fusion occurs. This is where hydrogen is converted into helium, releasing energy that powers the star. The core is incredibly hot, about 50–100 million Kelvin, and incredibly dense, with a density about 100 times that of water. The fusion reactions in the core occur through the proton-proton chain, the same process that powers the Sun. But in massive stars, there's also a more efficient process called the CNO cycle, carbon-nitrogen-oxygen cycle. Wait, but population 3 stars don't have carbon, nitrogen, or oxygen. This is true initially, but it doesn't remain true for long. As the star burns hydrogen into helium, trace amounts of heavier elements are produced as byproducts of the fusion reactions. These trace amounts are enough to catalyze the CNO cycle, which then becomes the dominant fusion process. The CNO cycle is much more temperature sensitive than the proton-proton chain. It produces energy at a rate proportional to the temperature to the 16th power compared to the 4th power for the proton-proton chain. This means the energy generation is concentrated in a very small region at the very center of the star. Surrounding the core is the radiative zone, where energy is transported outward by radiation. Photons produced in the core are absorbed and re-emitted countless times as they work their way outward through the dense stellar material. This random walk of photons is very slow. It can take hundreds of thousands of years for a photon to travel from the core to the surface. In the outer layers of the star is the convective zone, where energy is transported by convection. Hot gas rises, cools, and sinks back down, carrying energy with it. The convective zone is turbulent, with large-scale circulation patterns. For population 3 stars, the convective zone is relatively thin or may not exist at all. This is because the high luminosity and the efficiency of radiative transport mean that radiation can carry away the energy without needing convection. Finally, at the surface is the photosphere, the layer from which light escapes into space. This is what we would see if we looked at the star from the outside. The photosphere has a temperature of about 100,000 Kelvin, giving the star a blue-white color. Above the photosphere is the stellar atmosphere, including the chromosphere and corona. These outer layers are heated by magnetic fields and shock waves, reaching temperatures of millions of Kelvin. They're the source of stellar winds, streams of particles flowing away from the star at high speeds. Living fast, dying young. The most massive stars live the shortest lives. This might seem counterintuitive. You might think a more massive star with more fuel would live longer. But the opposite is true, because massive stars burn their fuel much faster. The lifetime of a star is roughly proportional to its mass divided by its luminosity. Since luminosity scales as mass to the 4th power, the lifetime scales as mass to the -3rd power. This means a star that's 10 times more massive lives about 1,000 times shorter. The Sun, with a mass of 1 solar mass and a luminosity of 1 solar luminosity, will live for about 10 billion years. A star with 100 solar masses and a luminosity of 100 million solar luminosities will live for only about 2 to 3 million years. This is incredibly short by cosmic standards. The first stars formed when the universe was about 100 to 200 million years old. They died when the universe was only 100 to 203 million years old. They were a brief flash in cosmic time, living and dying in what amounts to an instant compared to the current age of the universe. But in that brief time, they had an enormous impact. They transformed the universe, creating the first heavy elements, ionizing the surrounding gas and setting in motion the processes that would lead to the formation of galaxies and later generations of stars. The Eddington limit, a fundamental constraint. There's a fundamental limit on how luminous a star can be, called the Eddington limit. This limit arises from the balance between gravity, which pulls matter inward, and radiation pressure, which pushes matter outward. When a star's luminosity exceeds the Eddington limit, the radiation pressure becomes strong enough to overcome gravity, and the star's outer layers are blown away. This sets an upper limit on the luminosity, and therefore on the mass, of stars. The Eddington limit depends on the star's mass and composition. For a star made of pure hydrogen, the Eddington luminosity is ARID 30,000, AT Sun X, M Sun, where M is the star's mass, and M Sun is the mass of the Sun. For a 100 solar mass star, the Eddington luminosity is about 3 million solar luminosities. This is roughly consistent with the luminosities predicted for population 3 stars, suggesting that these stars were close to the Eddington limit. Stars near the Eddington limit are unstable. Small perturbations can cause the luminosity to exceed the Eddington limit, temporarily driving mass loss. This might explain why the most massive stars have strong stellar winds. They're constantly shedding mass to stay below the Eddington limit. For the first stars, being near the Eddington limit meant they were constantly fighting against their own radiation. The intense radiation pressure tried to blow the star apart, while gravity tried to hold it together. This created a dynamic, unstable situation where the star's outer layers were constantly being pushed and pulled. Some of the most massive first stars might have been super Eddington. Their luminosity exceeded the Eddington limit. These stars would have been extremely unstable, with strong mass loss and possibly pulsations. They might have shed a significant fraction of their mass during their short lives. Stellar winds. The breath of giants. All stars lose mass through stellar winds, streams of particles flowing away from the star's surface. The Sun has a stellar wind, though it's quite weak, carrying away only about 10 or 14 solar masses per year. But massive stars have much stronger stellar winds. The wind strength increases rapidly with luminosity, scaling roughly as the luminosity to the 1.5 power. For the most massive first stars, the mass loss rate could have been 10 or 25 to 10 or 4 solar masses per year, a billion times stronger than the Sun's wind. At this rate, a 200 solar mass star could lose 20 to 40 solar masses over its 2 to 3 million year lifetime. This is a significant fraction of the star's total mass, and it would have important consequences for the star's evolution and ultimate fate. The stellar winds from the first stars were driven primarily by radiation pressure. Photons from the star's intense radiation field were absorbed by atoms in the stellar atmosphere, transferring momentum to them and accelerating them outward. Once accelerated, these atoms collided with other atoms, dragging them along and creating a wind. This process is most efficient when there are heavy elements in the atmosphere to absorb the photons. But population 3 stars initially had no heavy elements. How could they drive winds? The answer is that even trace amounts of heavy elements, produced by fusion in the star's core and mixed into the atmosphere by convection or other processes, were enough to drive winds. Additionally, hydrogen and helium can also absorb photons, though less efficiently, contributing to the wind. The winds from the first stars had important effects on their surroundings. They pushed gas away from the stars, creating cavities and shells. They enriched the surrounding gas with the trace amounts of heavy elements produced in the stars. And they carried away angular momentum, potentially affecting the rotation of the stars. Rotation, spinning giants. Stars rotate, and rotation can have important effects on their structure and evolution. The Sun rotates slowly, with a rotation period of about 25 days at the equator. But some stars rotate much faster, with rotation periods of only hours. How fast did the first stars rotate? This is an important question because rotation affects many aspects of stellar evolution. Shape. Rapidly rotating stars are flattened at the poles and bulge at the equator due to centrifugal force. Mixing. Rotation can drive mixing between the core and the envelope, bringing fresh fuel to the core and extending the star's lifetime. Mass loss. Rotation enhances mass loss, especially near the equator where the centrifugal force partially counteracts gravity. Magnetic fields. Rotation can generate magnetic fields through a dynamo process. The rotation rate of the first stars depended on how much angular momentum they acquired during formation. As we discussed in the previous chapter, the collapsing gas clouds had some angular momentum due to tidal torques. This angular momentum was partially transferred to the forming stars. Computer simulations suggest that the first stars were probably rotating at moderate rates, not extremely fast but not negligibly slow either. A typical rotation period might have been a few days to a few weeks, giving a rotation speed of about 500 kilometers per second at the equator. This is fast enough to have noticeable effects on the star's structure and evolution, but probably not fast enough to make the star unstable or to dominate its evolution. The first stars were likely not spinning giants in the sense of rotating at breakup speed, but they were rotating fast enough to matter. Terrain. Magnetic fields. The hidden force. Magnetic fields play important roles in many astrophysical phenomena, from stellar winds to the formation of jets. But did the first stars have magnetic fields? In modern stars, magnetic fields are generated by a dynamo process, the motion of electrically conducting fluid, plasma, in the star's interior generates electric currents, which in turn generate magnetic fields. This process requires rotation and convection. For population 3 stars, the situation is uncertain. If they had convective zones and if they were rotating, they could have generated magnetic fields through a dynamo. But as we mentioned earlier, the convective zones in population 3 stars were probably thin or absent, which might have limited the dynamo. On the other hand, there are other mechanisms that can generate magnetic fields. The Taylor-Spruitt dynamo, for example, can operate in radiative zones, generating magnetic fields even without convection. And magnetic fields might have been present in the gas from which the stars formed, either as primordial fields from the early universe or fields generated during the collapse. If the first stars did have magnetic fields, these fields would have affected their evolution in several ways. Angular momentum transport. Magnetic fields can transport angular momentum from the core to the envelope, affecting the star's rotation profile. Mass loss. Magnetic fields can enhance mass loss by channeling the stellar wind along magnetic field lines. Mixing. Magnetic fields can drive mixing between different layers of the star, affecting the chemical composition. Stability. Magnetic fields can affect the stability of the star, potentially suppressing or enhancing instabilities. The strength and structure of magnetic fields in population 3 stars remain uncertain, and this is an active area of research. Future simulations with more sophisticated magnetic field modeling will help us understand this better. The interior lives of stars. Inside a population 3 star, nuclear fusion is converting hydrogen into helium at a prodigious rate. Let's understand this process in more detail. The primary fusion reaction is 4H, He4, plus energy. This reaction converts 4 hydrogen nuclei, protons, into 1 helium-4 nucleus, 2 protons and 2 neutrons, releasing about 26.7 MeV, million electron volts, of energy. This energy is released in the form of photons and neutrinos. The photons are absorbed by the surrounding stellar material, heating it and creating the pressure that supports the star against gravity. The neutrinos escape directly from the star without interacting, carrying away a small fraction of the energy. The conversion of hydrogen to helium occurs through a chain of reactions. In the proton-proton chain, the main pathway is 1. Two protons fuse to form deuterium, heavy hydrogen, releasing a positron and a neutrino. 2. The deuterium captures another proton, forming helium. 3. Two helium-3 nuclei fuse, forming helium-4 and releasing 2 protons. In the CNO cycle, carbon, nitrogen, and oxygen act as catalysts. 1. Carbon-12 captures a proton, forming nitrogen-13. 2. Nitrogen-13 decays to carbon-13, releasing a positron and a neutrino. 3. Carbon-13 captures a proton, forming nitrogen-14. 4. Nitrogen-14 captures a proton, forming oxygen-15. 5. Oxygen-15 decays to nitrogen-15, releasing a positron and a neutrino. 6. Nitrogen-15 captures a proton, forming carbon-12 and helium-4. The net result is the same as the proton-proton chain. 4 protons are converted into 1 helium-4 nucleus, but the CNO cycle is much more efficient at high temperatures. As the star burns hydrogen in its core, the composition of the core gradually changes. Hydrogen is depleted and helium accumulates. Eventually, the core will run out of hydrogen and the star will have to find a new source of energy. But that's a story for a later chapter. The photosphere, the star's visible face. When we look at a star, what we see is the photosphere, the layer from which light escapes into space. For population 3 stars, the photosphere was incredibly hot, about 100,000 Kelvin. At this temperature, the star emits most of its light in the ultraviolet part of the spectrum. If we could see ultraviolet light with our eyes, a population 3 star would appear as a brilliant blue-white point of light, far brighter than any star, visible in the night sky today. The spectrum of light from the photosphere tells us about the star's composition and physical conditions. When light passes through the stellar atmosphere, atoms in the atmosphere absorb light at specific wavelengths, creating dark absorption lines in the spectrum. For population 3 stars, the spectrum would be dominated by hydrogen and helium lines, with no lines from heavy elements, at least initially. This is the signature we're looking for when we search for population 3 stars, a spectrum showing only hydrogen and helium with no metals. The photosphere is also the source of the stellar wind. Atoms in the photosphere absorb photons from the star's radiation field, gaining energy and momentum. If they gain enough energy, they can escape from the star's gravity, contributing to the wind. The photosphere is not a sharp boundary. It's a gradual transition from the opaque interior of the star to the transparent space around it. The thickness of this transition region is only about 1% of the star's radius, so for practical purposes, we can think of the photosphere as a surface. Nadir, the chromosphere, and corona. Above the photosphere are the chromosphere and corona, the outer layers of the stellar atmosphere. These layers are much hotter than the photosphere, reaching temperatures of millions of Kelvin. This might seem paradoxical. How can the outer layers be hotter than the inner layers? The answer is that these layers are heated by mechanisms other than radiation from below. Magnetic fields and shock waves carry energy from the photosphere to the chromosphere and corona, heating them to extreme temperatures. In the sun, the corona is visible during solar eclipses as a faint glow extending far beyond the visible disk. It's the source of the solar wind and of spectacular phenomena like coronal mass ejections. For population 3 stars, the chromosphere and corona were probably even more extreme than the sun's due to the higher luminosity and stronger magnetic fields. They might have been the source of very strong stellar winds and energetic outbursts. The corona is also the source of X-rays. Hot gas in the corona emits X-rays, which can escape from the star and travel through space. These X-rays could have important effects on the surrounding gas, ionizing it and heating it. Decay, pulsations, and instabilities. Massive stars are often unstable to pulsations, periodic expansions and contractions of the star's outer layers. These pulsations are driven by the same mechanism that powers Cepheid variable stars. The opacity of the stellar material varies with temperature, creating a feedback loop that drives oscillations. Population 3 stars might have been particularly prone to pulsations because of their high luminosity and proximity to the Eddington limit. Small perturbations could trigger pulsations, causing the star's brightness to vary periodically. These pulsations could have important consequences. Mass loss. Pulsations can enhance mass loss by periodically lifting the star's outer layers to greater heights, where they're more easily blown away by radiation pressure. Mixing. Pulsations can drive mixing between different layers of the star, affecting the chemical composition. Observability. Pulsations cause the star's brightness to vary, which could make population 3 stars easier to detect if we could observe them. Some of the most massive population 3 stars might have been unstable to more violent instabilities, such as the pair instability that we'll discuss in a later chapter. These instabilities could cause the star to explode, ending its life in a spectacular supernova. The first stars in context. Let's step back and appreciate what we've learned about the first stars. They were massive, 100 to 1,000 times more massive than the Sun. They were luminous, 1 million to 10 million times more luminous than the Sun. They were hot, with surface temperatures of 100,000 Kelvin. They were short-lived, living only 2 to 3 million years. And they were chemically pure, composed only of hydrogen and helium, with no heavy elements. These properties made them fundamentally different from stars in the modern universe. They were titans, giants among stars, burning bright and dying young. But they were also pioneers. They were the first stars to shine in the universe, ending the Dark Ages and beginning the epoch of reionization. They were the first to create heavy elements, seeding the universe with the building blocks of planets and life. They were the first to explode as supernovae, enriching the intergalactic medium and triggering new waves of star formation. In the next chapter, we'll explore one of the most important roles of the first stars, cosmic alchemy. We'll see how nuclear fusion in the cores of these stars created the first heavy elements, transforming the chemical composition of the universe and opening up new possibilities for cosmic evolution. The forge of creation. In medieval times, alchemists sought to transform base metals into gold, to discover the elixir of life, to unlock the secrets of matter itself. They failed in their quest, but they were asking the right questions. How is matter transformed? Where do the elements come from? What are the fundamental building blocks of reality? Today, we know the answers to these questions, and remarkably, the true alchemy, the actual transformation of elements, doesn't occur in laboratories or mystical workshops. It occurs in the hearts of stars. Stars are the universe's alchemists, the cosmic forges where simple elements are transformed into complex ones. And the first stars were the first alchemists, creating the first heavy elements in a universe that had previously known only hydrogen and helium. This chapter is about that process, about how nuclear fusion in the cores of the first stars created carbon, oxygen, nitrogen, iron, and all the other elements that make up the periodic table. It's about how the first stars transformed the chemical composition of the universe, opening up new possibilities for cosmic evolution. This is the story of cosmic alchemy. Verper, the primordial composition. Let's begin by recalling the chemical composition of the universe before the first stars formed. As we discussed in earlier chapters, the Big Bang created only the 3 lightest elements. Hydrogen, H, about 75% by mass. Hydrogen is the simplest element, with 1 proton in its nucleus and 1 electron orbiting it. Helium, He, about 25% by mass. Helium has 2 protons and 2 neutrons in its nucleus, for helium-4, the most common isotope, with 2 electrons orbiting. Lithium, Li, about 0.01% by mass. Lithium-7 has 3 protons and 4 neutrons in its nucleus. There were also trace amounts of deuterium, heavy hydrogen with 1 proton and 1 neutron, and helium-3 with 2 protons and 1 neutron. That's it. Everything else, all the elements from carbon to uranium, all the atoms that make up planets, rocks, water, air, and living beings, didn't exist yet. The universe was chemically simple, composed almost entirely of the 2 lightest elements. This might seem like a severe limitation, but it was actually a temporary state. The first stars were about to change everything. Nuclear fusion, the power source of stars. To understand how stars create heavy elements, we need to understand nuclear fusion in more detail. Nuclear fusion is the process by which two atomic nuclei combine to form a heavier nucleus. This process releases energy because the resulting nucleus has less mass than the original nuclei. The missing mass has been converted to energy according to Einstein's famous equation, E mc2. But fusion doesn't happen easily. Atomic nuclei are positively charged because they contain protons, and like charges repel. To fuse two nuclei together, you have to overcome this electrical repulsion, bringing the nuclei close enough that the strong nuclear force, which attracts nuclei at very short distances, can bind them together. This requires extreme conditions, high temperature, so the nuclei are moving fast enough to overcome the repulsion, and high density, so collisions occur frequently. These conditions exist in the cores of stars, where temperatures reach millions of Kelvin and densities reach hundreds of times that of water. In the cores of the first stars, the primary fusion reaction was the conversion of hydrogen into helium. 4. H. He plus energy. This reaction releases about 0.7% of the mass as energy, a small fraction, but enormous in absolute terms. When 1 kilogram of hydrogen is converted to helium, about 7 grams of mass is converted to energy, releasing about 6 10 14 joules, enough energy to power a typical household for about 20,000 years. For a massive first star, converting hydrogen to helium at a rate of about 10^38 kilograms per second, about 500 million Earth masses per second. The energy release is about 4 to 10 or 31 watts, roughly 10 million times the sun's luminosity. This enormous energy release is what powers the star, creating the pressure that supports it against gravitational collapse. But it's also the first step in the process of creating heavy elements. Helium burning, creating carbon and oxygen. After a few million years of burning hydrogen, the core of a population 3 star runs out of hydrogen fuel. The core is now composed primarily of helium, the ash of hydrogen burning. With no fusion reactions to generate energy, the core begins to contract under gravity. This contraction releases gravitational energy, heating the core. The temperature rises from about 50 million Kelvin to about 100 million Kelvin. At this temperature, a new fusion reaction becomes possible: helium burning. Helium burning is more complex than hydrogen burning because helium nuclei are more strongly charged. They have 2 protons instead of 1, requiring higher temperatures to overcome the electrical repulsion. The primary reaction is 3 He, C plus energy. This is called the triple alpha process because it involves 3 helium-4 nuclei, alpha particles, combining to form carbon-12. The triple alpha process is remarkable for several reasons. First, it's a 3-body reaction. 3 particles must collide simultaneously, which is extremely rare. Second, it proceeds through an intermediate state, beryllium-8, that's unstable and decays in about 10^16 seconds. Third, it's enhanced by a resonance in the carbon-12 nucleus, a quantum mechanical effect that increases the reaction rate by a factor of about 10 million. This resonance was predicted by astronomer Fred Hoyle in 1954, before it was discovered experimentally. Hoyle realized that carbon is abundant in the universe, and the only way to explain this abundance was if there was a resonance that enhanced the triple alpha process. His prediction was confirmed by experiments, and it's now recognized as one of the great triumphs of theoretical astrophysics. Without this resonance, very little carbon would be produced in stars, and the universe would be very different, possibly unable to support life as we know it, since carbon is essential for organic chemistry. Once carbon is produced, it can capture another helium nucleus to form oxygen. C+, He, O+ energy. This reaction produces oxygen, 16, the most common isotope of oxygen. The balance between carbon and oxygen production depends on the temperature and density in the core and on the relative rates of the 2 reactions. In massive stars like the first stars, both carbon and oxygen are produced in significant quantities. Helium burning lasts for a much shorter time than hydrogen burning, only about 500,000 years for a 200 solar mass star compared to 2 to 3 million years for hydrogen burning. This is because helium burning releases less energy per unit mass than hydrogen burning, and because the star is more luminous during this phase. Advanced burning stages. Building heavier elements. After helium is exhausted in the core, the star faces another crisis. The core, now composed of carbon and oxygen, begins to contract again, heating up to even higher temperatures. If the star is massive enough, and the first stars certainly were, the core reaches temperatures high enough to ignite carbon burning, C plus C, Ne plus He plus energy, C plus C, Na plus H plus energy, Cc, Mg plus energy. These reactions produce neon, sodium, and magnesium, along with various other products. Carbon burning occurs at temperatures of about 600 million Kelvin and lasts for only about 10,000 years in a massive star. After carbon is exhausted, the core contracts again, and neon burning begins, Ne plus gram, O plus. This reaction is actually a photodisintegration. A high-energy photon, Gr, breaks apart a neon nucleus into oxygen and helium. The helium can then be captured by other nuclei, building heavier elements. Neon burning occurs at about 1.2 billion Kelvin and lasts for only about 1 year. Next comes oxygen burning, O plus O, Psi plus He plus energy, O plus O, P plus H plus energy, O plus O, S plus energy. This produces silicon, phosphorus, and sulfur. Oxygen burning occurs at about 1.5 billion Kelvin and lasts for only about 6 months. Finally, silicon burning begins, C plus Gran, Mg plus He, followed by many reactions building heavier elements. Silicon burning is actually a complex network of reactions that build elements all the way up to iron. It occurs at temperatures of about 3 billion Kelvin and lasts for only about 1 day. Each successive burning stage occurs at higher temperature, releases less energy, and lasts for a shorter time. The star is racing through its nuclear fuel, desperately trying to generate enough energy to support itself against gravity. The iron peak, the end of fusion. The fusion process can't continue indefinitely. There's a fundamental limit, and it occurs at iron. Iron 56 is the most stable nucleus in the universe. It has the highest binding energy per nucleon. The most energy is required to break it apart, and the most energy is released when it's formed from lighter nuclei. This means that fusing nuclei lighter than iron releases energy, but fusing nuclei heavier than iron requires energy. Stars can't generate energy by fusing iron into heavier elements. They would have to put energy in, which would cool the core rather than heating it. When the core of a massive star is converted to iron, fusion stops. There's no more nuclear fuel to burn. The core can no longer generate energy to support itself against gravity. This is the beginning of the end for the star. But it's also the beginning of something new, the creation of elements heavier than iron through a different process. For the first stars, the buildup of an iron core marked a critical transition. The star had spent its entire life fighting against gravity, using nuclear fusion to generate the energy needed to support itself. Now, with fusion no longer possible, gravity would finally win. But before we discuss what happens next, let's understand how elements heavier than iron are created. Beyond iron. Neutron capture elements. Heavier than iron can't be created by fusion during normal stellar evolution. They're created by a different process, neutron capture. Neutron capture occurs when a nucleus captures a neutron, forming a heavier isotope of the same element. If this heavier isotope is unstable, it can undergo beta decay, converting a neutron into a proton and emitting an electron. This transforms the nucleus into a different element with one more proton. There are 2 main neutron capture processes. The S process, slow process. This occurs in the late stages of evolution of low to intermediate mass stars. Neutrons are produced at a slow rate, and nuclei capture them one at a time, with beta decays occurring between captures. This process builds elements up to lead and bismuth. The R process, rapid process. This occurs in explosive environments like supernovae and neutron star mergers. Neutrons are produced at a very high rate, and nuclei capture many neutrons in rapid succession before beta decay can occur. This process can build elements all the way up to uranium and beyond. For the first stars, the R process was probably the dominant mechanism for creating elements heavier than iron. When these stars exploded as supernovae, as we'll discuss in the next chapter, the extreme conditions in the explosion produced enormous numbers of neutrons, allowing the R process to operate efficiently. This R process nucleosynthesis created elements like gold, platinum, uranium, and thorium, elements that are rare but important, both for their practical uses and for their role in understanding cosmic history. The onion structure. As a massive star goes through successive burning stages, it develops a layered structure like an onion. Each layer consists of the ash of the previous burning stage. Core. Iron and iron peak elements, nickel, cobalt. Silicon burning shell, silicon fusing to iron, oxygen burning shell, oxygen fusing to silicon, neon burning shell, neon fusing to oxygen. Carbon burning shell, carbon fusing to neon and magnesium, helium burning shell, helium fusing to carbon and oxygen, hydrogen burning shell, hydrogen fusing to helium, envelope, unburned hydrogen and helium. This onion structure is a consequence of the temperature gradient in the star. The center is hottest, so the most advanced burning occurs there. Moving outward, the temperature decreases and earlier burning stages occur. For a 200 solar mass population 3 star near the end of its life, this onion structure might look like iron core, 10 solar masses, radius 1,000 kilometers, silicon shell, 5 solar masses, radius 10,000 kilometers, oxygen shell, 10 solar masses, radius 100,000 kilometers. Carbon shell, 20 solar masses, radius 1 million kilometers, helium shell, 50 solar masses, radius 10 million kilometers, hydrogen envelope, 105 solar masses, radius 100 million kilometers. These numbers are approximate and depend on many factors, including the star's initial mass, rotation rate, and mass loss history. But they give a sense of the structure. This onion structure is crucial for understanding what happens when the star dies. When the iron core collapses, as we'll discuss in the next chapter, the collapse sends a shock wave outward through these layers, triggering explosive burning and ejecting the layers into space. Mixing and dredge up. The onion structure I just described is somewhat idealized. In reality, there's mixing between the layers, driven by convection, rotation, and other processes. Convection occurs when a region of the star becomes unstable to overturning motions. Hot gas rises, cool gas sinks, and material is mixed between different layers. This can bring products of nuclear burning from the core to the envelope, or bring fresh fuel from the envelope to the core. Rotation can also drive mixing. Differential rotation, where different parts of the star rotate at different rates, creates shear, which can generate turbulence and mixing. Rotation can also drive meridional circulation, large-scale flows from the poles to the equator and back, which transports material between different layers. For population 3, stars, mixing was probably important because of their high rotation rates and strong convection. This mixing could have affected the chemical composition of the star's envelope, bringing products of nuclear burning to the surface. If heavy elements were mixed to the surface, they could be ejected into space by stellar winds. This would enrich the surrounding gas with heavy elements even before the star exploded as a supernova. This process, called chemical feedback, might have been important for the early chemical enrichment of the universe. Even if only a small fraction of the heavy elements produced in the core were mixed to the surface and ejected by winds, this could have significantly affected the composition of the next generation of stars. The chemical yield. The total amount of heavy elements produced by a star is called its chemical yield. This depends on the star's mass, composition, and evolution. For population 3 stars, the chemical yield was substantial. A 200 solar mass star might produce helium, 50 solar masses, carbon, 5 solar masses, oxygen, 10 solar masses, neon, 3 solar masses, magnesium, 1 solar mass, silicon, 2 solar masses, iron, 5 solar masses, other elements, 1 solar mass. These numbers are approximate and depend on many factors, but they show that a single massive first star could produce significant amounts of heavy elements, enough to enrich a large volume of gas to a composition that would affect the formation of the next generation of stars. The chemical yield also depends on how much of the star is ejected into space. If the star collapses to form a black hole, some of the heavy elements might be locked inside the black hole, never to be released. But if the star explodes as a supernova, most or all of the heavy elements can be ejected. The pattern of element abundances, which elements are produced in what quantities, is a signature of the nucleosynthesis process. By measuring the abundances of elements in old stars and gas clouds, we can infer what kinds of stars produced those elements. For example, if we find a star with lots of carbon and oxygen but little iron, it might have been enriched by a massive star that exploded as a pair instability supernova, which we'll discuss in the next chapter. If we find a star with lots of iron but little carbon and oxygen, it might have been enriched by a different type of supernova. These abundance patterns are like fingerprints, telling us about the history of nucleosynthesis in the early universe. The odd-even effect. One interesting feature of nucleosynthesis is the odd-even effect. Elements with even atomic numbers, carbon, oxygen, neon, magnesium, silicon, sulfur, etc., are more abundant than elements with odd atomic numbers, nitrogen, fluorine, sodium, aluminum, phosphorus, chlorine, etc. This occurs because nuclei with even numbers of protons and neutrons are more stable than nuclei with odd numbers. This is due to a quantum mechanical effect called pairing. Protons and neutrons like to pair up, and nuclei with all their nucleons paired are more stable. During nucleosynthesis, the more stable nuclei are produced more readily and survive longer before being converted to other nuclei. This creates the odd-even effect we observe. The odd-even effect is visible in the abundance pattern of elements in the universe. When we plot the abundance of elements versus atomic number, we see a zigzag pattern, with even-numbered elements more abundant than their odd-numbered neighbors. This pattern is a signature of nuclear physics, a reminder that the abundances of elements are determined by the fundamental properties of atomic nuclei. The alpha elements. Certain elements are called alpha elements because they're built up by successive captures of alpha particles, helium-4 nuclei. These include carbon, 3 alphas, oxygen, 4 alphas, neon, 5 alphas, magnesium, 6 alphas, silicon, 7 alphas, sulfur, 8 alphas, argon, 9 alphas, calcium, 10 alphas. These elements are produced in abundance in massive stars, particularly during helium burning and the subsequent burning stages. They're important tracers of massive star nucleosynthesis. When we observe old stars in our galaxy, we often find that they're alpha-enhanced. They have more alpha elements relative to iron than the Sun does. This tells us that these stars formed from gas that was enriched primarily by massive stars, before lower-mass stars, which produce more iron relative to alpha elements, had time to contribute significantly to the chemical enrichment. For the first generation of stars after population 3, called population 2 stars, we expect strong alpha enhancement because they were enriched only by massive population 3 stars. This is indeed what we observe, providing evidence that the first stars were massive. CNO, the building blocks of life. 3 elements are particularly important for life as we know it: carbon, nitrogen, and oxygen, CNO. These elements form the basis of organic chemistry, the chemistry of life. Carbon is the backbone of organic molecules, able to form long chains and complex structures. Nitrogen is essential for amino acids and nucleic acids. Oxygen is essential for water and for many biological molecules. Before the first stars, none of these elements existed. The universe was sterile, incapable of supporting life. The first stars changed this. Through nuclear fusion, they created carbon, nitrogen, and oxygen, seeding the universe with the building blocks of life. Carbon was produced primarily during helium burning. Nitrogen was produced through the CNO cycle during hydrogen burning and through other reactions during later burning stages. Oxygen was produced during helium burning and later stages. When the first stars died and ejected these elements into space, they enriched the surrounding gas. This enriched gas could then form new stars and planets, and eventually, life. In this sense, the first stars were the ancestors of all life in the universe. Without them, we wouldn't exist. The carbon in our cells, the nitrogen in our DNA, the oxygen we breathe, all of it was created in stars, beginning with the first stars. Metals in astronomy. Astronomers use the term metals in a peculiar way. In astronomy, a metal is any element heavier than helium. This includes actual metals like iron and copper, but also nonmetals like carbon, oxygen, and nitrogen. This unconventional definition reflects the fact that, from an astrophysical perspective, hydrogen and helium are fundamentally different from all other elements. Hydrogen and helium were created in the Big Bang, while all other elements were created in stars. The fraction of a star's mass that consists of metals is called its metallicity, usually denoted Z. The Sun has a metallicity of about Z 0.02, meaning about 2% of its mass is elements heavier than helium. Population 3 stars, by definition, have Z.00. They contain no metals at all, or at most, trace amounts produced by their own nuclear burning. The metallicity of a star affects many of its properties. Opacity. Metals increase the opacity of stellar material, affecting how radiation is transported through the star. Cooling. Metals provide efficient cooling, affecting the temperature of star-forming gas clouds. Mass loss. Metals enhance stellar winds by providing more targets for radiation pressure. Planet formation. Metals are essential for forming rocky planets. The increase in metallicity over cosmic time, as successive generations of stars create and eject heavy elements, is one of the fundamental aspects of cosmic chemical evolution. The first metals in the universe. When the first stars died and ejected their heavy elements into space, they created the first metals in the universe. This was a transformative moment in cosmic history. The ejected metals mixed with the surrounding hydrogen and helium gas, creating a new generation of gas clouds with a composition different from the primordial composition. These clouds had metallicities of perhaps Z or 10 or 5 to 10 or 3, much lower than the Sun, but much higher than 0. This small amount of metals had a big impact. The metals provided efficient cooling, allowing gas clouds to cool to lower temperatures and fragment more efficiently. This meant the next generation of stars could be less massive than the first stars. The metals also affected the opacity of the gas, changing how radiation was transported, and they provided the raw material for forming dust grains, which would later play important roles in star and planet formation. The first metals also opened up new possibilities for chemistry. With carbon, nitrogen, and oxygen available, molecules like CO, H2O, and NH3 could form. These molecules would later be important for the chemistry of planet formation and the origin of life. In short, the first metals transformed the universe from a simple, chemically homogeneous state to a complex, chemically diverse state. They opened up new pathways for cosmic evolution, pathways that would eventually lead to planets, life, and intelligence. Observing the chemical signatures. How do we know about the nucleosynthesis that occurred in the first stars? We can't observe the first stars directly. They died billions of years ago. But we can observe their chemical signatures in later generations of stars. When we observe very old metal-poor stars in our galaxy, we're seeing stars that formed from gas enriched by only a few earlier generations of stars, possibly including population 3 stars. By measuring the abundances of elements in these stars, we can infer what kinds of stars enrich the gas from which they formed. For example, if we find a star with a very unusual abundance pattern, say, lots of carbon but little iron, this might indicate it was enriched by a single population 3 star with unusual properties. By studying many such stars and comparing their abundance patterns to theoretical predictions, we can build up a picture, of what the first stars were like and how they enriched the universe. This is a powerful technique called stellar archaeology, and it's one of the main ways we learn about the first stars. It's like being a detective, piecing together clues from the present to reconstruct events in the distant past. The legacy of cosmic alchemy. The first stars were cosmic alchemists, transforming simple elements into complex ones. Through nuclear fusion in their cores, they created carbon, oxygen, nitrogen, iron, and all the other elements that make up the periodic table. This cosmic alchemy was essential for the evolution of the universe. Without it, the universe would have remained chemically simple, composed only of hydrogen and helium. There would be no rocky planets, no water, no organic molecules, no life. The first stars gave the universe chemical complexity. They seeded space with heavy elements, enriching the gas from which later generations of stars and planets would form. They opened up new possibilities for cosmic evolution, possibilities that would eventually lead to us. In the next chapter, we'll see what happened when the first stars died. We'll witness their spectacular deaths as supernovae, the most energetic explosions in the universe. We'll see how these explosions dispersed the heavy elements created by nucleosynthesis, enriching the cosmos and triggering new waves of star formation. The first stars lived fast and died young, but their legacy lives on in every atom of every element, heavier than helium in the universe today. The final days. Every star must die. It's an inevitable consequence of the laws of physics. Stars generate energy by converting mass to energy through nuclear fusion, and eventually they run out of fuel. When that happens, the star can no longer support itself against gravity, and it must undergo a dramatic transformation. For the first stars, death came quickly. After only 2 to 3 million years of life, a mere blink of an eye in cosmic time, these massive giants exhausted their nuclear fuel and faced their final crisis. But the death of the first stars was not an end. It was a transformation, a rebirth. When these stars died, they didn't simply fade away. They exploded in the most energetic events in the universe, supernovae that released more energy in a few seconds than the sun will release in its entire 10 billion year lifetime. These explosions dispersed the heavy elements created by nucleosynthesis, enriching the cosmos with the building blocks of planets and life. They sent shock waves rippling through space, compressing gas clouds and triggering new waves of star formation. They created exotic objects like neutron stars and black holes, opening up new chapters in the story of the universe. This chapter is about the death of the first stars and the rebirth they enabled. It's about how destruction led to creation, how endings led to new beginnings. The iron core catastrophe. As we discussed in the previous chapter, massive stars go through successive burning stages, creating heavier and heavier elements in their cores. The final stage produces iron, the most stable nucleus in the universe. When the core is converted to iron, fusion stops. Iron can't be fused into heavier elements in a way that releases energy. It would require energy input instead. The core can no longer generate energy to support itself against gravity. For a brief time, the iron core is supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. This pressure can support the core even without fusion, but only up to a certain mass, called the Chandrasekhar limit, about 1.4 solar masses. As more iron is produced by silicon burning in the shell surrounding the core, the iron core grows. When it exceeds the Chandrasekhar limit, electron degeneracy pressure can no longer support it. The core collapses. This collapse is catastrophic. In less than a second, the core shrinks from a radius of about 1,000 kilometers to a radius of about 10 kilometers, a factor of 100 reduction in size. The density increases from about 10 grams per cubic centimeter to about 10 or 14 grams per cubic centimeter, a factor of 10,000 increase. This is one of the most extreme events in the universe, comparable in violence only to the Big Bang itself. The collapse process. Let's follow the collapse in detail, second by second. 2 seconds. The iron core exceeds the Chandrasekhar limit. Electron degeneracy pressure can no longer support it. The core begins to collapse. Picao 0.1 seconds. The core is collapsing at about 70,000 kilometers per second, nearly 1/4 the speed of light. The density and temperature are rising rapidly. At these extreme conditions, two processes occur that accelerate the collapse. 1. Photodisintegration. High-energy photons break apart iron nuclei into helium nuclei and neutrons. This process absorbs energy, cooling the core and removing pressure support. 2. Electron capture. Electrons are captured by protons, converting them into neutrons and neutrinos. This reduces the number of electrons, reducing the electron degeneracy pressure. Both processes accelerate the collapse, creating a runaway situation. At 5 seconds. The core has collapsed to a radius of about 50 kilometers. The density is now about 10^12 grams per cubic centimeter, comparable to the density of an atomic nucleus. The core is becoming a giant atomic nucleus composed primarily of neutrons. 0.5 seconds. The inner core reaches nuclear density, about 2^10^14 grams per cubic centimeter. At this density, the strong nuclear force becomes repulsive, providing a new source of pressure. The inner core suddenly becomes incompressible. The infalling outer core slams into this incompressible inner core at a significant fraction of the speed of light. The collision creates a shock wave that propagates outward through the star. 0.6 seconds. The shock wave is moving outward through the outer core and into the overlying layers of the star. As it moves outward, it heats the material it passes through, potentially triggering explosive nuclear burning. But the shock wave is losing energy. As it passes through the dense material of the outer core, it must do work to push the material outward against gravity. It also loses energy to the photodisintegration of heavy nuclei. For many years, computer simulations showed that the shock wave would stall. It would lose so much energy that it couldn't reach the surface of the star. The supernova would fail, and the star would collapse to form a black hole without producing a visible explosion. This was a major puzzle in supernova theory. We observe supernova, so they must work somehow, but simulations showed they shouldn't work. What was missing? Neutrinos to the rescue. The answer turned out to be neutrinos. During the collapse, enormous numbers of neutrinos are produced, about 1058 neutrinos in total, carrying away about 10^53 ergs of energy. That's a 1, followed by 53 zeros. This is about 100 times more energy than the sun will radiate in its entire lifetime, released in just a few seconds. Most of these neutrinos escape from the star without interacting with anything. Neutrinos interact very weakly with matter, so they can pass through the entire star as if it weren't there. But very weakly doesn't mean not at all. In the extreme densities of the collapsing core, even neutrinos can be trapped. They diffuse outward slowly, taking seconds to escape rather than passing through instantly. As they diffuse outward, a small fraction of them, about 1%, are absorbed by the material behind the stalled shock wave. This deposits energy into the material, heating it and creating pressure that pushes the shock wave outward. This neutrino heating is the key to successful supernovae. It provides the extra energy needed to revive the stalled shock wave and drive it outward through the star. Modern simulations that include neutrino heating show that supernovae can work. The shock wave can reach the surface of the star and produce a visible explosion. But it's a delicate balance, and the details depend on many factors, including the mass of the star, its rotation rate, and the physics of neutrino interactions. The explosion. Once the shock wave is revived by neutrino heating, it propagates outward through the star, taking about an hour to reach the surface. As the shock wave passes through the various layers of the star, the silicon shell, oxygen shell, carbon shell, helium shell, and hydrogen envelope, it heats them to billions of Kelvin. At these temperatures, explosive nuclear burning occurs. In the oxygen shell, oxygen fuses rapidly to silicon and sulfur. In the carbon shell, carbon fuses to neon and magnesium. In the helium shell, helium fuses to carbon and oxygen. These explosive burning processes create additional heavy elements and release additional energy, strengthening the shock wave. When the shock wave reaches the surface of the star, it breaks through and the star begins to explode. Material is ejected into space at speeds of 10,000 to 30,000 kilometers per second, up to 10% the speed of light. The explosion is incredibly luminous. At its peak, a supernova can outshine an entire galaxy, releasing about 10 to the power 51 ergs of kinetic energy, the energy of the ejected material, and about 1049 ergs of electromagnetic radiation, light. For a few weeks, the supernova is visible across vast distances. If a population 3 supernova occurred in a nearby galaxy today, it would be easily visible to the naked eye, appearing as a new bright star in the sky. But the first supernovae occurred when the universe was only a few 100 million years old, billions of light years away from where we are now. We can't see them directly. Their light has long since passed us by. But we can see their effects in the chemical composition of later generations of stars and in the large-scale structure of the universe. Pair instability. Supernovae, a special case for the most massive first stars, those with initial masses above about 140 solar masses. A different type of supernova can occur, a pair instability supernova. In the cores of these extremely massive stars, the temperature becomes so high that photons have enough energy to spontaneously create electron-positron pairs, pair production. This process removes energy from the core, reducing the pressure. The reduced pressure causes the core to contract, which heats it up, which produces more energetic photons, which create more pairs, which reduces the pressure further. This creates a runaway instability. The core contracts rapidly, heating up to the point where oxygen burning ignites explosively throughout the entire core. The energy released by this explosive burning is so great that it completely disrupts the star. There's no remnant left behind, no neutron star or black hole. The entire star is blown apart. Pair instability supernovae are even more energetic than normal core collapse supernovae, releasing up to 1052 ergs of kinetic energy, 10 times more than a typical supernova. They also produce distinctive abundance patterns with lots of oxygen and other alpha elements, but relatively little iron. These supernovae might have been common among the first stars because the first stars were so massive. They would have had a significant impact on the early chemical enrichment of the universe. Interestingly, there's a mass range, roughly 100 to 140 solar masses, where stars are too massive for normal core collapse supernovae, but not massive enough for pair instability supernovae. These stars might undergo pulsational pair instability, where the pair instability causes the star to pulsate violently, ejecting its outer layers in a series of eruptions before finally collapsing to form a black hole. The fate of a first star thus depends critically on its mass. 140 solar masses, core collapse supernova leaving a neutron star or black hole, 260 solar masses, pair instability supernova, complete disruption, above 260 solar masses, direct collapse to a black hole, possibly with weak or no supernova. These mass ranges are approximate and depend on factors like rotation and mass loss, but they give a sense of the variety of possible fates. The supernova remnant. After the explosion, the ejected material expands outward, creating a supernova remnant. This remnant consists of the heavy elements created by nucleosynthesis, now dispersed into space. The remnant expands at high speed, plowing into the surrounding gas and creating a shock wave. This shock wave heats the gas to millions of Kelvin, causing it to emit X-rays. The supernova remnant also creates a bubble of hot, low-density gas. This bubble can be hundreds of light years across, much larger than the original star. It's a region where the gas has been swept up and compressed by the expanding shock wave. Over time, the remnant cools and slows down. After about 10,000 years, it merges with the surrounding interstellar medium, dispersing the heavy elements throughout a large volume of space. These heavy elements mix with the primordial hydrogen and helium, creating a new generation of gas clouds with a composition different from the primordial composition. These enriched clouds will eventually form new stars. stars of the second generation with metallicities higher than 0. For the first supernovae, the remnants expanded into gas that was still relatively dense. The universe was younger and smaller, so the average density was higher. This meant the remnants didn't expand as far as modern supernova remnants before merging with the surrounding gas. But even so, a single first supernova could enrich a region of space thousands of light years across, affecting the formation of hundreds or thousands of second-generation stars. Chemical enrichment, the gift of the first stars. The most important legacy of the first supernova was chemical enrichment, the dispersal of heavy elements into the surrounding gas. Before the first supernovae, the universe was chemically pristine, composed of only hydrogen, helium, and trace lithium. After the first supernovae, the universe contained carbon, oxygen, nitrogen, iron, and all the other elements of the periodic table. This chemical enrichment had profound consequences. Cooling. Heavy elements provide efficient cooling, allowing gas clouds to cool to lower temperatures. This reduces the gene's mass, allowing smaller stars to form. The second generation of stars was less massive than the first generation because of this enhanced cooling. Dust formation. Heavy elements can condense into solid grains, dust, which plays important roles in star and planet formation. Dust provides additional cooling, shields molecules from destructive radiation, and serves as the building blocks of rocky planets. Molecular chemistry. With heavy elements available, complex molecules can form. Molecules like CO, H2O, and NH3 become possible, opening up new pathways for chemical evolution. Planet formation. Rocky planets require heavy elements, silicon, iron, magnesium, and others. Before the first supernovae, rocky planets couldn't form. After the first supernovae, planet formation became possible. Life. Life as we know it requires heavy elements, particularly carbon, nitrogen, oxygen, and phosphorus. Before the first supernovae, life was impossible. After the first supernovae, the building blocks of life were available. In this sense, the first supernovae were the events that made the modern universe possible. They transformed the cosmos from a simple chemically homogeneous state to a complex chemically diverse state capable of producing planets and life. Triggering new star formation. Supernova explosions don't just enrich the gas with heavy elements, they also trigger new star formation. The shock wave from a supernova compresses the gas it encounters. If this compression is strong enough, it can push the gas above the threshold for gravitational collapse, triggering the formation of new stars. This process, called triggered star formation, is important in the modern universe. Many star-forming regions show evidence of being triggered by nearby supernovae or stellar winds. For the first supernovae, triggered star formation might have been even more important. The first stars formed in isolated dark matter halos, separated by large distances. Without some mechanism to spread star formation from one halo to another, star formation would have proceeded very slowly. Supernova-triggered star formation provided such a mechanism. When a first star exploded, its shock wave could propagate to nearby halos, compressing the gas and triggering the formation of second-generation stars. This created a chain reaction. The first stars formed, exploded, triggered the formation of second-generation stars, which in turn formed and exploded, triggering third-generation stars, and so on. Star formation spread from halo to halo, gradually filling the universe with stars. This process also helped to mix the heavy elements. Each supernova enriched a region of space, and the next generation of stars formed from this enriched gas. Over time, the metallicity of the universe increased as more and more supernovae occurred. Feedback, regulating star formation. While supernovae can trigger star formation, they can also suppress it. This is another example of feedback, the process by which stars affect their environment. The energy released by a supernova heats the surrounding gas to millions of Kelvin. Hot gas has high pressure and is difficult to compress. This means that gas heated by a supernova is unlikely to form stars. It's too hot and too diffuse. Supernova feedback can thus regulate star formation, preventing all the gas from turning into stars at once. This is important for understanding galaxy formation and evolution. In the early universe, supernova feedback from the first stars might have been particularly important. The first stars formed in small, dark matter, hollows with relatively shallow gravitational potential wells. The energy from a single supernova might have been enough to blow all the gas out of the halo, preventing any further star formation in that halo. This would have created a self-limiting process. The first stars formed, exploded, and blew the gas out of their halos. The gas would then flow into larger halos, where it could cool and form new stars. Over time, star formation would shift from small halos to larger halos, eventually leading to the formation of galaxies. This process is still not fully understood, and it's an active area of research. Computer simulations are helping to clarify how supernova feedback affected the early universe and how it influenced the formation of the first galaxies. Neutron stars. The compact remnants. When a massive star explodes as a supernova, not all of its mass is ejected. The core remains behind, compressed to extreme density by the collapse. If the core has a mass between about 1.4 and 3 solar masses, it becomes a neutron star, an object composed almost entirely of neutrons, with a radius of only about 10 kilometers, but a mass comparable to the Sun. Neutron stars are among the most extreme objects in the universe. Density. About 10-14 grams per cubic centimeter, comparable to the density of an atomic nucleus. A teaspoon of neutron star material would weigh about 1 billion tons. Gravity. The surface gravity is about 10-11 times stronger than Earth's. If you could stand on a neutron star, you couldn't, you'd be crushed instantly. You would weigh about 100 billion times more than you do on Earth. Magnetic fields. Neutron stars can have magnetic fields trillions of times stronger than Earth's. These fields can accelerate particles to nearly the speed of light, creating beams of radiation that sweep across space as the neutron star rotates. Rotation. Neutron stars can rotate incredibly fast, up to hundreds of times per second. This rapid rotation is a consequence of conservation of angular momentum. As the core collapsed, it spun faster, like a figure skater pulling in their arms. Some neutron stars are observed as pulsars, objects that emit regular pulses of radio waves as their beams of radiation sweep past Earth. The first pulsar was discovered in 1967, and thousands have been discovered since. Did the first stars leave behind neutron stars? Probably, though we haven't observed any yet. Neutron stars from the first stars would be very old, about 13 billion years, and they might have cooled down enough that they are no longer visible as pulsars. But they might still be detectable through other means. If a first-star neutron star is in a binary system with another star, it might accrete matter from that star, heating up and emitting X-rays. Or if two first-star neutron stars merge, they would produce gravitational waves that might be detectable with future gravitational wave observatories. Black holes. That's ultimate remnants. If the core of a collapsing star has a mass greater than about 3 solar masses, even neutron degeneracy pressure can't support it. The core continues to collapse, shrinking without limit, forming a black hole. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. It's defined by its event horizon, the boundary beyond which escape is impossible. For a non-rotating black hole, the radius of the event horizon is r/2gm(c2), where g is the gravitational constant, m is the mass of the black hole, and c is the speed of light. For a 10 solar mass black hole, the event horizon has a radius of about 30 kilometers. Black holes are even more extreme than neutron stars. Density. Formally infinite at the center, the singularity, though quantum effects probably prevent true infinities. Gravity. Strong enough to trap light itself. Time dilation. Time passes more slowly near a black hole due to gravitational time dilation. An observer falling into a black hole would appear to freeze at the event horizon from the perspective of a distant observer. Black holes from the first stars would have masses of about 10 to 100 solar masses, depending on the mass of the original star and how much mass was ejected in the supernova, if there was a supernova at all. These first black holes are important for several reasons. Gravitational wave sources. When two black holes merge, they produce gravitational waves, ripples in spacetime that propagate at the speed of light. The LIGO and Virgo observatories have detected dozens of black hole mergers, and some of these might involve black holes from the first stars. Seeds of supermassive black holes. The centers of most galaxies contain supermassive black holes with masses of millions to billions of solar masses. How did these supermassive black holes form? One possibility is that they grew from seed black holes left behind by the first stars. Accretion and feedback. Black holes can accrete matter from their surroundings, releasing energy in the process. This accretion can produce powerful jets and radiation, affecting the surrounding gas and regulating star formation. The first black holes might have played important roles in the formation and evolution of the first galaxies, though the details are still being worked out. The diversity of fates. Not all first stars died in the same way. Depending on their mass, rotation, and other properties, they could have had very different fates. Low-mass first stars, 25-40 solar masses. Core collapse supernova with relatively low energy, leaving a neutron star. Moderate chemical enrichment. Intermediate mass first stars, 40-140 solar masses. Energetic core collapse supernova, possibly leaving a black hole. Significant chemical enrichment with a mix of elements. High mass first stars, 140-260 solar masses. Pair instability supernova, complete disruption with no remnant. Very high chemical enrichment with distinctive abundance patterns, lots of oxygen, less iron. Very high mass first stars, above 260 solar masses. Direct collapse to a black hole with little or no supernova, minimal chemical enrichment. Rapidly rotating first stars. Might produce gamma-ray bursts, the most energetic explosions in the universe, if they form black holes with accretion disks. This diversity of fates created a diversity of chemical enrichment patterns and feedback effects. Different regions of the early universe might have been enriched by different types of first stars, leading to different conditions for second-generation star formation. The cosmic cycle. The death of the first stars was not an end. It was part of a cycle. A cosmic cycle of birth, death, and rebirth that continues to this day. Stars form from gas clouds. They live, burning nuclear fuel and creating heavy elements. They die, ejecting those heavy elements into space. The enriched gas forms new stars, which create more heavy elements, die, and enrich the gas further. The cycle continues, with each generation of stars building on the legacy of previous generations. This cosmic cycle is why the universe has evolved from simple to complex, from chemically homogeneous to chemically diverse, from sterile to life-bearing. The first stars were the beginning of this cycle. They were the first to form, the first to create heavy elements, the first to die and enrich the cosmos. Every star that came after them, including our Sun, is part of this cosmic cycle, part of the ongoing process of chemical evolution. In the next chapter, we'll explore how the first stars shaped the large-scale structure of the universe. We'll see how their radiation ionized the surrounding gas, creating bubbles of transparency in an otherwise opaque cosmos. We'll see how these bubbles grew and merged, eventually ionizing the entire universe. And we'll see how this process, called reionization, transformed the universe and set the stage for the formation of galaxies. The first stars didn't just create heavy elements, they transformed the universe itself. Illuminating the universe. The first stars did more than create heavy elements. They transformed the very nature of the universe itself. Their intense ultraviolet radiation ionized the hydrogen gas that filled space, changing it from neutral to ionized, from opaque to transparent. This transformation, called cosmic reionization, was one of the major phase transitions in the history of the universe, comparable in importance to recombination, when the universe first became transparent, and the Big Bang itself. Before reionization, the universe was filled with neutral hydrogen gas that absorbed ultraviolet light. After reionization, the universe was filled with ionized hydrogen plasma that was transparent to ultraviolet light. This change affected everything from the formation of galaxies to the propagation of light across cosmic distances. But reionization wasn't a sudden uniform process. It began with the first stars, creating small bubbles of ionized gas around each star. These bubbles grew and merged, gradually ionizing larger and larger regions. The process took hundreds of millions of years, transforming the universe from a neutral state to an ionized state. This chapter is about that transformation. It's about how the first stars illuminated the universe, creating the cosmic web of ionized gas that we see today. It's about how light conquered darkness, how order emerged from chaos, how the universe evolved from simple to complex. The neutral universe. Let's begin by understanding what the universe was like before reionization. After recombination, about 380,000 years after the Big Bang, the universe became neutral. Electrons combined with protons to form hydrogen atoms, and the universe became transparent to the cosmic microwave background radiation. But this transparency applied only to the CMB photons, which had energies too low to ionize hydrogen. For higher energy photons, ultraviolet photons with energies above 13.6 electron volts, the ionization energy of hydrogen, the universe was opaque. Any ultraviolet photon traveling through the neutral hydrogen gas would quickly be absorbed by a hydrogen atom, ionizing it. The free electron would then recombine with a proton, emitting a new photon. This photon might be reabsorbed by another hydrogen atom, and the process would repeat. The net effect was that ultraviolet light couldn't travel far through the neutral universe. It was absorbed and re-emitted many times, diffusing slowly rather than propagating freely. This had important consequences. It meant that even if there were sources of ultraviolet light in the early universe, and there weren't until the first stars formed, that light couldn't travel far. The universe was dark, not just because there were no stars, but also because even if there were stars, their light couldn't escape. The neutral universe was also cold. Without sources of energy to heat it, the gas cooled as the universe expanded. By the end of the Dark Ages, the gas temperature had dropped to about 20-30 Kelvin, cold enough that the gas could cool and collapse to form stars, but also cold enough that the universe was a very different place from what it is today. The first ionizing photons. When the first stars ignited, they began producing enormous numbers of ultraviolet photons. A typical first star with a surface temperature of 100,000 Kelvin emitted most of its light in the ultraviolet part of the spectrum. These ultraviolet photons had energies well above the 13.6 eV needed to ionize hydrogen. When they encountered neutral hydrogen atoms, they ionized them, splitting them into protons and electrons, but the ionized gas didn't immediately recombine back into neutral atoms. The density of the gas was low enough that recombination was slow. An ionized hydrogen atom, a proton and a free electron, would typically remain ionized for thousands to millions of years before recombining. This meant that the ionizing photons from the first stars could create regions of ionized gas, HII regions, around each star. These regions would persist for a long time, growing as more and more photons were emitted by the star. Let's calculate how large these HII regions could grow. A typical first star emitted about 10 to 50 ionizing photons per second. Over its lifetime of 2 to 3 million years, it would emit about 10 to 63 ionizing photons. Each photon could ionize one hydrogen atom. The number density of hydrogen atoms in the early universe was about 0.1 atoms per cubic centimeter. The universe was denser then than it is now. If all the photons went into ionizing hydrogen, the HII region would have a volume of about 10 to 64 cubic centimeters, corresponding to a radius of about 1,000 light-years. In reality, the HII region would be somewhat smaller because 1. Some photons are absorbed by recombining hydrogen atoms rather than ionizing new atoms. 2. Some photons escape from the HII region without being absorbed. 3. The density of hydrogen is higher near the star, so the HII region doesn't expand as far. But even accounting for these effects, the HII region around a first star could be hundreds of light years across, much larger than the star itself. The growth of HII regions. The growth of an HII region is governed by a competition between ionization, photons ionizing neutral hydrogen, and recombination, protons and electrons recombining to form neutral hydrogen. In the early stages, when the HII region is small, ionization dominates. The star is producing photons faster than the gas can recombine, so the HII region expands rapidly. As the HII region grows, it encounters more and more hydrogen atoms. The rate of recombination increases because there are more ionized atoms that can recombine. Eventually, the HII region reaches an equilibrium size where the rate of ionization equals the rate of recombination. This equilibrium size is called the Strömgren radius, named after astronomer Bengt Strömgren, who first calculated it in 1939. For a first star in the early universe, the Strömgren radius is about 100 to 1,000 light years, depending on the star's luminosity and the density of the surrounding gas. But the HII region doesn't stop growing at the Strömgren radius. As the universe expands, the density of the gas decreases, which decreases the recombination rate. This allows the HII region to grow beyond the Strömgren radius. Additionally, if multiple stars form in the same region, their HII regions can overlap, creating a larger combined HII region. This is important because the first stars probably formed in small groups rather than in isolation. Over time, the HII regions around the first stars grew to sizes of thousands of light years, creating bubbles of ionized gas in the otherwise neutral universe. Sharper. The ionization front. The boundary of an HII region is called the ionization front, the interface between ionized gas on the inside and neutral gas on the outside. The ionization front is not a sharp boundary, it's a transition region, typically a few light years thick, where the gas changes from fully ionized to fully neutral. The ionization front can move in two ways: R-type, radiation-dominated ionization front. This occurs when the ionizing photons can penetrate into the neutral gas faster than the gas can recombine. The ionization front moves outward at nearly the speed of light, ionizing the gas as it goes. D-type, density-dominated ionization front. This occurs when the recombination rate is high enough that the ionizing photons are absorbed close to the ionization front. The ionization front moves outward more slowly, at a speed determined by the balance between ionization and recombination. For the first stars, the ionization fronts were initially R-type, expanding rapidly as the star turned on. But as the HII region grew and the density of neutral hydrogen at the ionization front decreased, the fronts transitioned to D-type, expanding more slowly. The ionization front is also a shock front. It compresses the neutral gas ahead of it, creating a dense shell. This compression can trigger star formation in the neutral gas, creating a new generation of stars at the edge of the HII region. This process, called radiation-driven implosion, might have been important for spreading star formation in the early universe. The first stars created HII regions, which compressed the surrounding gas, which triggered the formation of second-generation stars, which created their own HII regions, and so on. The temperature of ionized gas. Ionized gas is much hotter than neutral gas. When a photon ionizes a hydrogen atom, any excess energy, beyond the 13.6 eV needed for ionization, goes into the kinetic energy of the free electron. This heats the gas. For photons from a first star with energies of 20 to 100 eV, the excess energy is substantial. The ionized gas is heated to temperatures of about 10,000 to 20,000 Kelvin, much hotter than the 20 to 30 Kelvin of the neutral gas. This heating has important consequences. Pressure. Hot gas has high pressure, which resists gravitational collapse. This makes it harder for gas in HII regions to form stars. Sound speed. The sound speed in the gas increases with temperature. In hot ionized gas, the sound speed is about 10 kilometers per second, compared to about 0.3 kilometers per second in cold neutral gas. Gene's mass. The gene's mass, the minimum mass for gravitational collapse, increases with temperature. In hot ionized gas, the gene's mass is about 10 mph solar masses compared to about 10 mph solar masses in cold neutral gas. These effects mean that ionization by the first stars suppress star formation in the ionized regions. This is another example of negative feedback. The first stars prevented the formation of additional stars nearby by ionizing and heating the gas. But this feedback wasn't entirely negative. The hot ionized gas could flow out of the small dark matter halos where the first stars formed into larger halos where it could cool and form new stars. This helped to shift star formation from small halos to larger halos, eventually leading to the formation of galaxies. Overlapping HII regions. As more and more first stars formed, their HII regions began to overlap. When two HHII regions met, they merged into a single larger HII region. This process of merging created increasingly large ionized regions. Where the first stars were clustered together in the densest nodes of the cosmic web, the HII regions merged quickly, creating large ionized bubbles. In regions where the first stars were more spread out, the HII regions remained isolated for longer, eventually merging as they grew. Computer simulations of reionization show that the process was highly inhomogeneous. Some regions became ionized early, while others remained neutral for much longer. The ionized regions were concentrated along the filaments of the cosmic web, where the density of dark matter and gas was highest, and where the first stars formed most readily. Between the filaments were voids, regions of low density where few stars formed. These voids remained neutral longer, eventually being ionized by radiation from the surrounding filaments. The result was a complex web-like pattern of ionized and neutral regions, with ionized bubbles growing and merging along the filaments, gradually filling in the voids. This pattern is sometimes called the Swiss cheese model of reionization. The universe was like a block of Swiss cheese, with ionized bubbles, the holes, growing in a neutral medium, the cheese, eventually merging until the neutral regions were reduced to isolated pockets. The epoch of reionization. The process of reionization didn't happen all at once. It occurred gradually, over a period of hundreds of millions of years. The epoch of reionization is usually defined as the period when the universe transitioned from mostly neutral, more than 50% neutral, to mostly ionized, more than 50% ionized. Based on observations, this epoch occurred roughly between 200 million and 1 billion years after the Big Bang. The timeline of reionization can be divided into several phases. Early phase, 100–300 million years. The first stars form and create small G regions. The universe is still mostly neutral, but the first ionized bubbles are appearing. Middle phase, 300–700 million years. More stars form, Chi regions grow and begin to overlap. The ionized fraction increases from a few percent to about 50%. This is the main epoch of reionization. Late phase, 700 million, 1 billion years. The HII regions have merged into large ionized regions. The universe is mostly ionized with only isolated neutral pockets remaining. These pockets are gradually ionized, completing the reionization process. Post-reionization, after 1 billion years. The universe is fully ionized. Ongoing star formation maintains the ionization, preventing the gas from recombining. The exact timing of these phases is still uncertain and is an active area of research. Different observations give slightly different results, and there's ongoing debate about when reionization began and ended. But the general picture is clear. Reionization was a gradual process driven by the cumulative effect of many generations of stars, beginning with the first stars and continuing for hundreds of millions of years. The role of galaxies. While the first stars initiated reionization, they probably didn't complete it. The first stars were rare and short-lived, and their HII regions, while large, covered only a small fraction of the universe. To fully ionize the universe required many more sources of ionizing photons. These sources were the first galaxies, collections of millions to billions of stars forming when the universe was a few 100 million years old. Galaxies are much more efficient at producing ionizing photons than individual stars because they contain many stars. A typical early galaxy might contain 10^6 to 10^9 stars, producing 10 or 56 to 10^59 ionizing photons per second, millions to billions of times more than a single star. The HAI regions around galaxies could be thousands to millions of light-years across, much larger than the HAI regions around individual stars. As galaxies formed and evolved, they produced more and more ionizing photons, creating larger and larger HII regions. These HII regions merged, gradually ionizing the entire universe. The transition from star-dominated to galaxy-dominated reionization probably occurred around 200 to 300 million years after the Big Bang, when the first galaxies began to form in significant numbers. But the first stars were still important because they initiated the process. They created the first ionized bubbles, they enriched the gas with heavy elements, allowing more efficient star formation in galaxies, and they might have helped to trigger galaxy formation through their feedback effects. Observing reionization. How do we know about reionization? We can't observe it directly. It occurred billions of years ago, and we can't see the individual HI regions or ionization fronts. But we can observe the effects of reionization in several ways. The cosmic microwave background. Reionization affected the CMB through a process called Thomson's scattering. When CMB photons pass through ionized gas, they can scatter off free electrons, changing their direction and polarization. By measuring the polarization of the CMB, we can infer when reionization occurred. Observations from the Planck satellite suggest that reionization was mostly complete by about 1 billion years after the Big Bang. Quasar spectra. Quasars are two extremely luminous objects powered by supermassive black holes. When we observe distant quasars, we see absorption lines in their spectra caused by neutral hydrogen along the line of sight. By studying these absorption lines, we can measure how much neutral hydrogen existed at different times. Observations show that the universe was mostly neutral before about 1 billion years after the Big Bang, and mostly ionized after that. The Lyman alpha forest. This is a series of absorption lines in quasar spectra caused by neutral hydrogen at different distances. The properties of the Lyman alpha forest tell us about the distribution of neutral hydrogen and the progress of reionization. 21 cm radiation. Neutral hydrogen emits radio waves at a wavelength of 21 centimeters. By mapping this 21 cm radiation from the early universe, we can directly observe the distribution of neutral hydrogen and watch reionization in progress. This is the goal of several current and future radio telescopes, including LOFAR, MWA, Hera, and SKA. High redshift galaxies. By observing galaxies that formed during the epoch of reionization, we can study the sources of ionizing photons and understand how they contributed to reionization. The James Webb Space Telescope is particularly well suited for this, as it can observe galaxies from the first billion years of cosmic history. These observations are gradually building up a detailed picture of reionization, though many questions remain unanswered. The topology of reionization. One of the interesting questions about reionization is its topology, the shape and connectivity of the ionized regions. Did reionization proceed inside out, with ionized bubbles forming around galaxies and growing outward? Or did it proceed outside in, with voids being ionized first and dense regions remaining neutral longer? The answer appears to be inside out. Ionized bubbles formed first in the densest regions, where galaxies were forming most rapidly. These bubbles grew and merged, gradually filling in the lower density regions. This inside-out topology is a consequence of the biased distribution of galaxies. Galaxies form preferentially in high-density regions, so these regions produce more ionizing photons and become ionized first. The topology of reionization also affects how it progressed. When ionized bubbles are small and isolated, they grow independently. But as they grow and begin to overlap, they merge and the growth accelerates. This creates a percolation transition, a sudden change from a state with many small bubbles to a state with a few large connected regions. This percolation transition might have occurred around the midpoint of reionization, when the ionized fraction reached about 50%. Before this point, the ionized regions were mostly isolated bubbles. After this point, the ionized regions were mostly connected with isolated neutral pockets. Understanding the topology of reionization is important for interpreting observations, particularly 21 cm observations, which are sensitive to the size and distribution of neutral regions. Brady or feedback effects. Reionization had important feedback effects on galaxy formation and evolution. Photoheating. The ionizing radiation heated the gas to 10,000–20,000 Kelvin. This increased the gene's mass, making it harder for gas to collapse and form stars in small halos. This suppressed star formation in halos with masses below about 10⁸ solar masses, affecting the abundance of dwarf galaxies. Photoevaporation. The hot ionized gas could flow out of small halos, evaporating their gas reservoirs and preventing further star formation. This is called photoevaporation, and it might explain why there are fewer dwarf galaxies than predicted by dark matter simulations. Pressure support. The pressure of the hot ionized gas provided support against gravitational collapse, affecting the structure of gas in galaxies and the intergalactic medium. These feedback effects created a complex interplay between reionization and galaxy formation. Galaxies produced the ionizing photons that drove reionization, but reionization affected the formation and evolution of galaxies, particularly small galaxies. This interplay is still not fully understood, and it's an active area of research. Computer simulations are helping to clarify how reionization and galaxy formation influenced each other. Chakrur. The end of reionization. Reionization ended when the universe became fully ionized, when the last neutral pockets were ionized and the universe transitioned to a state where nearly all hydrogen was ionized. This probably occurred around 1 billion years after the Big Bang, though the exact timing is uncertain. After this point, the universe remained ionized, maintained by ongoing star formation in galaxies. The end of reionization marked a major transition in cosmic history. Before reionization, the universe was neutral and opaque to ultraviolet light. After reionization, the universe was ionized and transparent to ultraviolet light. This transparency allowed light to travel freely across cosmic distances, making it possible to observe distant objects. Without reionization, we wouldn't be able to see distant quasars or galaxies. Their light would be absorbed by neutral hydrogen along the line of sight. Reionization also affected the thermal history of the universe. The heating associated with reionization raised the temperature of the intergalactic medium to about 10,000 Kelvin, where it has remained, with some evolution, to the present day. The cosmic web revealed. After reionization, the large-scale structure of the universe became visible in a new way. The ionized gas traced the cosmic web, the filaments and sheets of matter that connect galaxies. This ionized gas, called the intergalactic medium, IgM, is observable through its absorption of light from distant quasars. When we observe a distant quasar, we see absorption lines in its spectrum caused by the IgM along the line of sight. These absorption lines create the Lyman alpha forest we mentioned earlier. The Lyman alpha forest is a powerful tool for studying the cosmic web. By analyzing the absorption lines, we can map the distribution of gas in the IgM and study how it evolved over cosmic time. The IgM is not uniformly distributed. It's concentrated in filaments and sheets, with voids containing very little gas. This distribution reflects the underlying dark matter distribution and the history of structure formation. The IgM is also not uniformly ionized. While most of it is ionized, there are regions of higher density, where the recombination rate is high enough that some neutral hydrogen remains. These regions create stronger absorption lines in the Lyman alpha forest. By studying the IgM, we can learn about the processes that shape the universe. structure formation, reionization, galaxy formation, and feedback from stars and black holes. The first stars' lasting impact. The first stars initiated reionization, but their impact extended far beyond that. They created the first heavy elements, seeding the universe with the building blocks of planets and life, triggered the formation of second-generation stars through their supernova explosions and radiation, shaped the cosmic web through their feedback effects, affecting the distribution of gas and the formation of galaxies, ionized the universe, transforming it from neutral to ionized and making it transparent to ultraviolet light, left behind compact remnants, neutron stars and black holes that continue to affect the universe today. All of these effects stemmed from the first star's fundamental properties. They were massive, luminous, and short-lived. They burned bright and died young, but in their brief lives, they transformed the universe. In the final chapter, we'll explore the legacy of the first stars in more detail. We'll see how they set the stage for everything that came after: galaxies, planets, and life. We'll trace the connection from the first stars to us, showing how we are, in a very real sense, the descendants of those cosmic pioneers. The descendants of stars. We've journeyed through billions of years of cosmic history, from the Big Bang to the formation of the first stars, from their lives as cosmic titans to their deaths as spectacular supernovae, from their ionization of the universe to their shaping of the cosmic web. Now, in this final chapter, we'll explore the ultimate legacy of the first stars. We'll see how they set in motion a chain of events that led to everything we see in the universe today: galaxies, planets, and life. We'll trace the connection from those ancient cosmic pioneers to us, showing how we are made of star stuff, how we are the universe's way of knowing itself. This is the story of how the first star's legacy lives on, billions of years after they died. This is the story of how light conquered darkness, how complexity emerged from simplicity, how the universe evolved from a sterile expanse of hydrogen and helium to a cosmos teeming with galaxies, stars, planets, and life. This is the legacy of light. From first stars to galaxies. The first stars formed in isolation, in small, dark matter halos scattered throughout the universe. But they didn't remain isolated for long. As we discussed in previous chapters, the first stars had powerful feedback effects. Their radiation ionized and heated the surrounding gas. Their stellar winds pushed gas away. Their supernova explosions ejected heavy elements and sent shock waves rippling through space. These feedback effects had a paradoxical result. They suppressed star formation in the small halos where the first stars formed, but they enabled star formation in larger halos. Here's how it worked. The feedback from the first stars heated the gas and gave it energy. This hot, energetic gas could escape from small halos, which have shallow gravitational potential wells. But it couldn't escape from larger halos, which have deeper potential wells. So the gas flowed out of small halos and into larger halos. In these larger halos, the gas could cool, despite being heated by the first stars, and form new stars. These new stars formed in greater numbers than the first stars, creating the first galaxies. This process is called hierarchical structure formation, and it's a fundamental feature of cosmology. Small structures form first, then merge to form larger structures. Small halos form first, then merge to form larger halos. Small groups of stars form first, then merge to form galaxies. The first galaxies were small by modern standards, perhaps 10^6 to 10^8 solar masses, compared to 10^11 solar masses for the Milky Way. But they were the seeds from which all later galaxies grew. These early galaxies formed when the universe was only a few 100 million years old. They were irregular in shape, lacking the beautiful spiral structure of modern galaxies. They were actively forming stars at high rates, converting their gas into stars much faster than modern galaxies do. And they were enriched with heavy elements from the first stars. The second generation of stars that formed in these galaxies had metallicities of perhaps 10^5 to 10^3 solar metallicity, much lower than the Sun, but much higher than zero. This chemical enrichment had important consequences. It allowed the gas to cool more efficiently, enabling the formation of lower-mass stars. It allowed dust to form, which played important roles in star and planet formation, and it opened up new pathways for chemical evolution, allowing complex molecules to form. The buildup of galaxies. Over cosmic time, galaxies grew through two main processes: in situ star formation. Gas within the galaxy cooled and formed new stars. This process converted the galaxy's gas reservoir into stars, gradually building up the stellar mass. Mergers. Smaller galaxies merged together to form larger galaxies. This process added both stars and gas to the growing galaxy. Both processes were important, and their relative importance changed over cosmic time. In the early universe, when galaxies were small and gas-rich, in situ star formation dominated. Later, as galaxies grew larger and their gas reservoirs were depleted, mergers became more important. The Milky Way, our home galaxy, is the product of billions of years of this hierarchical buildup. It formed from the merger of many smaller galaxies, and it continues to accrete smaller galaxies today. The Sagittarius dwarf galaxy, for example, is currently being torn apart by the Milky Way's gravity, its stars being absorbed into the Milky Way's halo. When we look at the stars in the Milky Way, we can see evidence of this hierarchical buildup. The oldest stars, found in the galactic halo and in globular clusters, have low metallicities, indicating they formed early in cosmic history from gas that had been only slightly enriched by previous generations of stars. Some of these old stars might have been enriched by population 3 stars, the first stars. By studying the chemical composition of these ancient stars, we can learn about the first stars indirectly, even though the first stars themselves are long gone. The chemical evolution of galaxies. As galaxies evolved, their chemical composition changed. Each generation of stars created heavy elements through nucleosynthesis, then ejected those elements into the interstellar medium through stellar winds and supernova explosions. This process, called chemical evolution, gradually increased the metallicity of galaxies over cosmic time. The first galaxies had metallicities near zero. Modern galaxies like the Milky Way have metallicities around 1 to 2%, solar metallicity. The chemical evolution of galaxies is not uniform. Different elements are produced by different types of stars and on different timescales. Alpha elements, O, Mg, Psi, Ka, etc. Produced primarily by massive stars which live for only a few million years and explode as core collapse supernovae. These elements are produced early in a galaxy's history. Iron peak elements, Fe, Ni, Ko, etc. Produced by both massive stars and Type Ia supernovae, exploding white dwarfs. Type Ia supernovae occur later, after low-mass stars have had time to evolve, so iron peak elements are produced over a longer time scale. Neutron capture elements, Senior, Ba, U, etc. Produced by the R process in core collapse supernovae and neutron star mergers, and by the S process in evolved low-mass stars. These elements are produced over a range of timescales. By measuring the abundances of different elements in stars of different ages, we can reconstruct the chemical evolution history of galaxies. This is like being an archaeologist, piecing together the history of a civilization from the artifacts it left behind. For the Milky Way, this chemical archaeology reveals a complex history. The oldest stars are alpha-enhanced, indicating they formed from gas enriched primarily by massive stars, possibly including population 3 stars. Younger stars have lower alpha to iron ratios, indicating they formed from gas enriched by a mix of massive stars and Type Ia supernovae. This pattern is consistent with the hierarchical buildup scenario. The Milky Way formed from the merger of many smaller galaxies, each with its own chemical evolution history. The formation of the Milky Way. The Milky Way is a large spiral galaxy containing about 204 billion stars. It has a disk about 100,000 light-years in diameter and a few thousand light-years thick, with spiral arms winding outward from a central bulge. Surrounding the disk is a roughly spherical halo containing old stars and globular clusters. The Milky Way formed through the hierarchical buildup process we've been discussing. It began as many small proto-galaxies, each containing millions to billions of stars. These proto-galaxies merged together over billions of years, building up the Milky Way we see today. The oldest stars in the Milky Way, found in the halo and globular clusters, formed about 13 billion years ago, only about 800 million years after the Big Bang. These stars are metal-poor, with metallicities as low as 10 nanometer solar metallicity. Some of these ancient stars might have formed in the first galaxies, the direct descendants of the regions where the first stars formed. By studying these stars, we can learn about the conditions in the early universe and the properties of the first stars. The disk of the Milky Way formed later, about 10–12 billion years ago, as gas settled into a rotating disk and formed new stars. The disk stars are younger and more metal-rich than the halo stars, reflecting the chemical enrichment that occurred over cosmic time. The Milky Way continues to evolve today. It's still forming stars, though at a much lower rate than in the past, about 1 to 2 solar masses per year, compared to perhaps 10–100 solar masses per year in the early universe. It's still accreting smaller galaxies, adding their stars to the halo, and it's on a collision course with the Andromeda Galaxy, our nearest large neighbor, which will merge with the Milky Way in about 4 to 5 billion years. The Sun, a third-generation star. Our Sun formed about 4.6 billion years ago from a cloud of gas and dust in the Milky Way's disk. This cloud had been enriched by many previous generations of stars, giving it a metallicity of about 2%, much higher than the first stars, 0%, or even the oldest stars in the Milky Way, 0.2%. The Sun is sometimes called a third-generation star, meaning it formed from material that had been processed through at least 2 previous generations of stars. The first generation, population 3, created the first heavy elements. The second generation, population 2, created more heavy elements and enriched the interstellar medium. The third generation, population 1, which includes the Sun, formed from this enriched material. Every atom in the Sun heavier than helium was created in previous generations of stars. The carbon, oxygen, nitrogen, iron, and all the other heavy elements in the Sun were forged in the nuclear furnaces of ancient stars, some of which might have been among the first stars. When we look at the Sun, we're seeing the legacy of billions of years of stellar evolution stretching back to the first stars. The Sun is a living connection to the earliest epochs of cosmic history. The formation of planets. The heavy elements created by stars enabled a new possibility, the formation of planets. Planets require heavy elements, silicon, iron, magnesium, and others, to form their rocky cores and metallic cores. Gas giant planets like Jupiter also require heavy elements to form their cores, which then accrete hydrogen and helium gas. Before the first stars, planets couldn't form. The universe contained only hydrogen and helium, which can't form solid bodies, except at extremely low temperatures where hydrogen can freeze, but such conditions didn't exist in the early universe. After the first stars enriched the universe with heavy elements, planet formation became possible. The first planets probably formed in the first galaxies, around second-generation stars enriched by population 3 supernovae. Our solar system formed about 4.6 billion years ago from a cloud of gas and dust called the solar nebula. This nebula was enriched with heavy elements from previous generations of stars, allowing the formation of rocky planets like Earth and gas giants like Jupiter. The formation process began when the solar nebula collapsed under its own gravity, forming the Sun at the center and a rotating disk of gas and dust around it. In this disk, dust grains collided and stuck together, gradually building up larger and larger bodies, from dust grains to pebbles to boulders to planetesimals to planets. The inner solar system, where temperatures were high, formed rocky planets: Mercury, Venus, Earth, Mars. The outer solar system, where temperatures were low, formed gas giants: Jupiter, Saturn, and ice giants: Uranus, Neptune. Earth formed about 454 billion years ago through the accretion of planetesimals. It was initially molten due to the heat generated by impacts and radioactive decay. Over time, it cooled and differentiated, with heavy elements like iron sinking to form the core and lighter elements like silicon rising to form the mantle and crust. The Earth's composition reflects the composition of the solar nebula, which in turn reflects the nucleosynthesis that occurred in previous generations of stars. The iron in Earth's core was created in massive stars and ejected in supernova explosions. The silicon in Earth's mantle was created through alpha capture processes in massive stars. The oxygen in Earth's atmosphere and water was created through helium burning in massive stars. Every element in Earth except hydrogen and helium was created in stars. We are, quite literally, made of star stuff. The origin of life. Life, as we know it, requires several key ingredients. Liquid water, a solvent for biochemical reactions. Organic molecules, complex molecules based on carbon, including amino acids, nucleic acids, and lipids. Energy, to drive chemical reactions and maintain organization. Time. For evolution to occur, Earth provided all of these ingredients. It had liquid water on its surface thanks to its distance from the sun and its atmosphere. It had organic molecules delivered by comets and asteroids and synthesized in the atmosphere and oceans. It had energy from the sun, from geothermal heat, and from chemical reactions. And it had time, billions of years for life to emerge and evolve. The origin of life on Earth is still not fully understood, but we know it occurred relatively early in Earth's history. The oldest evidence for life dates to about 3.5 to 3.8 billion years ago, only about 700 to 1,000 million years after Earth formed. This early emergence of life suggests that the transition from non-living chemistry to living biology might be relatively easy, given the right conditions. If so, life might be common in the universe, arising on many planets with suitable conditions. But the key point for our story is that life requires heavy elements: carbon, nitrogen, oxygen, phosphorus, sulfur, and others. These elements didn't exist before the first stars. They were created through nucleosynthesis in stars and dispersed through supernova explosions. Without the first stars, life as we know it couldn't exist. The first stars created the chemical building blocks of life, making our existence possible. The evolution of life. Once life emerged on Earth, it evolved over billions of years, becoming increasingly complex and diverse. The first life forms were simple single-celled organisms similar to modern bacteria. They obtained energy from chemical reactions or from sunlight through photosynthesis, and they reproduced by dividing. Over time, these simple organisms evolved into more complex forms. About 2 billion years ago, eukaryotic cells emerged, cells with a nucleus and other internal structures. About 600 million years ago, multicellular organisms emerged, organisms composed of many cells working together. The evolution of life was driven by natural selection, the process by which organisms with advantageous traits are more likely to survive and reproduce, passing those traits to their offspring. Over many generations, this process can produce dramatic changes, transforming simple organisms into complex ones. About 500 million years ago, during the Cambrian explosion, there was a rapid diversification of life forms, producing most of the major animal groups we see today: fish, insects, mollusks, and many. Other groups appeared during this time. About 400 million years ago, plants and animals colonized the land, opening up new ecological niches. About 230 million years ago, dinosaurs appeared, dominating the land for about 165 million years before going extinct 66 million years ago. After the dinosaurs' extinction, mammals diversified and became the dominant land animals. About 6-7 million years ago, the lineage leading to humans split from the lineage leading to chimpanzees. About 300,000 years ago, modern humans, Homo sapiens, emerged in Africa. And about 10,000 years ago, humans developed agriculture, leading to the rise of civilization, technology, and science, including the science that allows us to understand our cosmic origins. We are made of star stuff. Every atom in your body, except for hydrogen, was created in a star. Let's trace the origins of some key elements. Hydrogen, created in the Big Bang about 13.8 billion years ago. The hydrogen in your body is primordial, dating back to the first minutes of cosmic time. Carbon, created through helium burning in massive stars, possibly including population 3 stars. The carbon in your body was forged in stellar furnaces billions of years ago. Nitrogen, created through the CNO cycle in stars and through other processes in massive stars. The nitrogen in your DNA was created in stars. Oxygen, created through helium burning in massive stars. The oxygen you breathe and the oxygen in water was created in stars. Phosphorus, created in massive stars and ejected in supernova explosions. The phosphorus in your bones and DNA was created in stellar explosions. Calcium, created through alpha capture processes in massive stars. The calcium in your bones was created in stars. Iron, created in massive stars and in type Ia supernovae. The iron in your blood was created in stellar explosions. When Carl Sagan said, "We are made of star stuff," he was being literally accurate. The atoms in our bodies were created in stars, some of which might have been among the first stars in the universe. This is one of the most profound insights of modern science. We are connected to the cosmos in a deep and fundamental way. We are not separate from the universe. We are part of it. We are the universe's way of knowing itself. The search for the first stars. Despite their importance, we have never directly observed a population 3 star. They existed billions of years ago and are long gone, their light having traveled across the universe and passed us by. But astronomers are actively searching for them, using several strategies. Direct observation. With powerful telescopes like the James Webb Space Telescope, we might be able to observe the first stars directly, or at least the first galaxies that contain them. JWST can observe objects from the first few 100 million years of cosmic history, potentially seeing galaxies that contain second-generation stars enriched by population 3 stars. Gravitational lensing. Massive galaxy clusters can act as gravitational lenses, magnifying the light from distant objects behind them. This magnification might allow us to see individual first stars or small groups of first stars that would otherwise be too faint to detect. Supernovae. If we could observe a population 3 supernova, it would have a distinctive spectrum showing no heavy elements, or only elements created by the star itself. Surveys are searching for such supernovae, though none have been definitively identified yet. Gamma-ray bursts. Some population 3 stars might have produced gamma-ray bursts when they died. These extremely energetic explosions might be detectable even at very large distances. Stellar archaeology. By studying the chemical composition of old metal-poor stars in our galaxy, we can infer the properties of the population 3 stars that enrich them. This indirect method has provided much of our current understanding of the first stars. Gravitational waves. When black holes from population 3 stars merge, they produce gravitational waves. LIGO and Virgo have detected dozens of black hole mergers, and some of these might involve black holes from the first stars. In the coming years and decades, we can expect major advances in our understanding of the first stars. New telescopes and new techniques will allow us to probe deeper into the early universe, potentially observing the first stars directly or detecting their signatures in various ways. The future of the universe. The first stars were the beginning of a process that continues today, the ongoing evolution of the universe through star formation, chemical enrichment, and galaxy formation. But this process won't continue forever. The universe is changing in ways that will eventually bring star formation to an end. The universe is expanding, and the expansion is accelerating due to dark energy. As the universe expands, galaxies are moving apart and the density of matter is decreasing. Eventually, in about 100 billion years, star formation will cease. The gas reservoirs of galaxies will be exhausted, and there will be no more raw material to form new stars. The last stars will form, live, and die, and then there will be no more stars. After that, the universe will gradually fade. The stars that exist will burn out one by one. First, the massive stars will die, then the intermediate mass stars, and finally, trillions of years in the future, the smallest stars will die. Eventually, the universe will be dark again, filled with dead stars, white dwarfs, neutron stars, and black holes, and cold gas. This is sometimes called the heat death of the universe, though it's more accurately a cold death. But even this is not the end. Over unimaginably long timescales, 10 on 100 years or more, even the dead stars will decay. Protons might decay if certain theories of particle physics are correct, causing white dwarfs and neutron stars to evaporate. Black holes will evaporate through Hawking radiation, slowly losing mass until they disappear in a final flash of radiation. And in the far future, the universe might be a cold, dark, empty expanse, with only occasional flashes of light from evaporating black holes breaking the darkness. But this is so far in the future, trillions upon trillions of years, that it's almost meaningless to us. For now, and for the foreseeable future, the universe is alive with stars, galaxies, and the ongoing process of cosmic evolution. Our place in the cosmic story. We've traced the story of the universe from the Big Bang to the present, from the first stars to us. What does this story tell us about our place in the cosmos? First, it tells us that we are connected to the universe in a deep and fundamental way. We are made of atoms created in stars. We live on a planet formed from the debris of stellar explosions. We exist because the first stars created the heavy elements necessary for life. Second, it tells us that we are part of an ongoing process of cosmic evolution. The universe has been evolving for 13.8 billion years, becoming more complex over time. Stars formed from simple gas, galaxies formed from stars, planets formed from the debris of stars, life formed on planets, and intelligence emerged from life. We are the latest chapter in this story of increasing complexity. We are the universe's way of knowing itself, of understanding its own history and nature. Third, it tells us that we are rare and precious. The conditions necessary for life are stringent. A planet in the habitable zone of a star with liquid water, organic molecules, and billions of years of stability. Such conditions might be common in the universe, or they might be rare. We don't know yet. But even if life is common, intelligence might be rare. And even if intelligence is common, technological civilization might be rare. We might be one of many civilizations in the universe, or we might be alone. Either way, we are precious. We are the product of billions of years of cosmic evolution, from the first stars to the present. We carry within us the legacy of those ancient cosmic pioneers. The legacy lives on. The first stars lived for only a few million years, but their legacy lives on, billions of years after they died. They created the first heavy elements, seeding the universe with the building blocks of planets and life. They ionized the universe, transforming it from neutral to ionized and making it transparent to ultraviolet light. They triggered the formation of the first galaxies, setting in motion the hierarchical buildup that led to galaxies like the Milky Way. They shaped the cosmic web, affecting the distribution of matter on the largest scales, and ultimately, they made our existence possible. Without the first stars, there would be no heavy elements, no planets, no life, no us. When we look up at the night sky and see the stars, we're seeing the descendants of the first stars, stars formed from gas enriched by countless previous generations, stretching back to the cosmic dawn. When we look at ourselves, we're seeing the legacy of the first stars, atoms created in stellar furnaces, assembled into living beings through billions of years of evolution. The first stars were the pioneers of cosmic evolution, the first to transform the simple universe of the Big Bang into the complex universe we inhabit today. They were the first light in the darkness, the first to shine after the long dark ages. Their light has long since faded, but their legacy lives on in every atom of every element heavier than helium, in every star and galaxy, in every planet and living being. We are the descendants of the first stars. We are made of star stuff. We are the universe's way of knowing itself. And that is the legacy of light. Epilogue: The Cosmic Perspective. We began this journey with a question. How did the first stars form? We've answered that question in detail, tracing the story from the Big Bang through the Dark Ages to the formation of the first stars and beyond. But in answering this question, we've discovered something more profound. We've discovered our place in the cosmic story. We've learned that we are not separate from the universe, but part of it. We are connected to the cosmos in ways both physical and profound. This cosmic perspective, the understanding of our place in the universe, is one of the great gifts of science. It shows us that we are part of something larger than ourselves, something ancient and vast and beautiful. It shows us that the universe is not static, but evolving. It has a history, stretching back 13.8 billion years to the Big Bang. And we are part of that history, the latest chapter in an ongoing story of cosmic evolution. It shows us that the universe is comprehensible. Through observation, experiment, and theory, we can understand how the universe works, how it evolved, how we came to be. This is a remarkable fact, that the universe has produced beings capable of understanding it, and it shows us that we are precious. We are the product of billions of years of cosmic evolution, from quantum fluctuations in the early universe to the first stars to galaxies to planets to life to intelligence. We are rare and valuable, worthy of preservation and celebration. As we look to the future, we carry with us the legacy of the first stars. We are made of the elements they created. We live in a universe they transformed. We exist because they existed. The first stars were the cosmic dawn, the first light after the darkness, and we are their descendants, carrying their light forward into the future. This is the story of how the first stars formed. This is the story of cosmic evolution. This is our story.